Okay, so my name is Kem Raj, and I work primarily I contribute to OpenEmbedded project, and I'm quite interested in RISC-V of late, and I've been working on various pieces in the software side for RISC-V for about year and a half now or more. So today I'm just going to cover what it is, and there's a lot of software work that has happened and what's the status, what all has been upstreamed into various open source projects, what works, what's happening these days. So I think that will be pretty much it. So feel free to ask questions or any comments, discussions when we talk about it. So how many of you have worked with RISC-V so far? Good, so we got only one guy. That's bad. So RISC-V, it's actually a new ISA, a relatively new ISA, came in from Berkeley. In 2010, two students started it as a summer project. They looked at various other ISAs that were out there, predominantly ARM, x86, and they were other factors like licensing and other things, so they thought of, wouldn't it be nice to have an instruction set that is written ground up and is made available to other communities free. And that's how it came along. So it started as a 3-month project, and then it developed into a larger project at the university. So it's having 32-bit, 64, and 128-bit instruction possibilities as of today. Primarily, it is little endian. You can, I think, have a big endian version too if you want to. The specs, actually, it's open spec, so you can go in on GitHub. They maintain a GitHub/RISC-V repositories for various kind of specs. So you can go and take a look at all the specifications. Some of them are now finalized. Some are still under works. So you can participate, contribute. If you have ideas, I see all the time discussions around various subsystems. People contributing to various pieces of those specs, and it's all discussed in open on mailing lists. So you can download the PDFs for all the specs and read through those. And some of those specs are now at a locked state. The user space specs, for example, is locked down. Some, like virtualization, is still being discussed. So there is a lot of inputs that you can contribute to if you are interested in the CPU side of things. So I pointed the link here. You go to the specifications, you can download any area of interest that you have. So the architecture came from University of Berkeley, but it then is now kind of shepherded by, or rather also promoted by, a foundation called RISC-V Foundation. And a lot of companies and organizations, they have joined it as a member. And what it provides is a common collaboration space for everyone to participate in not only specifications, but also the other pieces, especially around software, for example, to bring up software and discussions around those. So the ISA, actually, one of the things I want to talk about, how it differentiates itself from the previous CPUs, is that it's a scalable ISA. What that means is the core set of instructions is really small. I think it's less than 40. So you have the RISC 32-bit instruction set, RV32, which is kind of the minimal set. So if you were to design a microcontroller or something, that's all you need. You just implement that. You are not supposed to implement the whole shebang of all the instruction sets. that gives you a really simple set of instructions to work with. But then if you're designing more customized solution, you can go and add additional instruction implementations and get a more powerful compute engine that you are looking for. So it's a ground-up approach, which is very strong in my mind, that you can come up with a lot of hardware design that today we do in software. So I think that this is kind of an ISA that is required if you were to customize chips and yet have a common instruction set where the software still can be common, right? So it's a different approach where you can have different hardware underneath and have same Linux Debian distribution running on top, right? Think in a reverse manner where you can share same kind of software that you were to run on one across multiple RISC-V implementations. So there are certain extensions that are already defined. For example, you'll find it if you go through specs or other places in software, you'll have references to this. So they have the integer multiply, atomic instructions, compressed instructions. So if you're familiar with ARM and MIPS, for example, there is a 32-bit and 16-bit instruction set, which is more compressed for code size on embedded systems. It's a similar concept here. And then, of course, the single precision floating point and double precision floating point. And then you concatenate that together to see what's implemented in your CPU. So, for example, RV64 integer multiply, so likewise. So you will see this kind of concatenated string that will represent the CPU implementation you have. And generally, G stands for general, which is a short form for IMFAD. So why it is RV64GC is a representation for a common instruction set that is being used in Linux world, like primarily all the desktop distributions and other operating systems. They have agreed to use RV64GC, so that's kind of a general instruction set. But in embedded space, that might not be the case. You might have, various other implementations based on RV32i and other, all these extensions not being present there. So, so the upstreaming began somewhere around 2014 for software side. So primarily we'll cover software here. So one of the first patches that were sent out was for the auto tools, right, to support RISC-V tuples, and that began around in 2014. So a lot of work was done by students at university to get all the basic software up, and so the next in the line is usually tools, like tool chain. You need compilers, you need other libraries like the system C library and others. That was the next set of things that were upstream. So here there's a difference where architecture is in definition state, but all the support for the specs is already getting upstreamed into tools like GCC, Bootloaders, and others. So it's a very different approach than it was with the previous architectures, where ARM architecture existed forever before it was upstreamed into various tools. In fact, there were ports that were kept outside the tree, and there are still ports that are outside the tree for ARM, for MIPS, and it's a humongous amount of patches, like in thousands, that are maintained outside. So this here, all the changes were upstreamed. Basically, the target is always upstream into whatever upstream open source project it is. So Bootloaders got 2.28, got the support for the 64-bit ISA. GCC 7.0 got the full support. Similarly, glibc 227. So these are fairly recent releases, but they are out there in open now. So today, if you were to use a fairly modern tool chain, you can easily build a RISC-V tool chain just from upstream repositories. Yes? Yes, I'll talk about it, and actually I'm participating in there, so you can ask me more questions if you want, but yes, it is. The port is already available. It's not yet upstreamed. It is actually at the verge of being accepted. So hopefully, maybe in a few weeks, if everything is addressed that the maintainer has reviews for, maybe we'll get the 64-bit in first, and then maybe 32-bit a bit later. But yeah, it's in works. So as you can see, that these are the primary level of tools that I covered here, which gives you a hosted Linux tool chain. It gives you a bare metal tool chain, and it gives you an emulator and a debugger. So basically, by this, you have all the basic ingredients that you need to bootstrap a new architecture. Thereafter are your bootloaders, and so there are a few options that are out there, and few of them are already ported to RISC-V. Code boot was one of the initial ones, and U-boot got it recently, end of last year, and proxy kernel BBL, that was actually the original kind of a bootstrapper, I would say, from the university itself, and it was used, and I think Western Digital contributed the OpenSBI recently, which is basically replacing this implementation with a more standard implementation of a spec at a platform level, where all this like UFI and others, they can also speak the same language using the OpenSBI. So are you covering OpenSBI in your talk? Yeah. So I think there is another talk in the afternoon where I think you can get into more on that side. We have a lot more details on there. Grub is actually very new. So Grub got the port, RISC-V port got accepted into Grub, and it's probably going to be there in 2.04 release. So what that means is that all the desktop distributions, they use Grub. So it opens up, simplifies, the desktop distributions quite a lot. So it's a very positive thing in my mind that getting the support into Grub is a big thing. There is a UFI spec as well available. I don't think there is a implementation yet. Some folks from HPE were trying to do it. I'm not sure how far they have gotten to implement UFI. But we got Grub in there, and hopefully, next time when we meet, we will have more. So on the kernel sides, I'll cover a little bit of Linux and then some of the RTOSes on high level. 4.15 is when the API, the user-based API, was submitted and accepted upstream, which means all the SysCalls and all the like spec-based user APIs, they were accepted and submitted. Although we still used forks because driver work was still happening, and 4.15 was still not usable from upstream as much, but now starting I think 5.x, I think you can boot a Hi-Fi board, which is a Freedom U540. I think you can just build it directly from upstream kernel.org kernel, and it will have most of the support, hopefully. It's usable, I would say. That you still have patches on the Sci5 kernel fork, but they have upstreamed quite a lot of it. Like hard SWCaps got recently submitted into 5.1, and so likewise, they are moving all the fixes that they're carrying for long into upstream kernels. So majority of work was done by University of California at Berkeley, Sci5 and Andes technology to do all the kernel support. The work has been happening since 2011 and 10, so it is not that it's scrambled work. So this has gone through a lot of testing, at a local level. So the patches were there. They made them better and better, upstream worthy, and now they're upstream. So Zephyr, as you might know, is one of the RTOS options that are out there. Zephyr is a project under Linux Foundation, and actually this was fairly early in, I think a year or so ago, that somebody submitted the port for Zephyr. And actually Zephyr is deployed now in real RISC-V chips, microcontrollers, of course. So there are a bunch of microcontrollers that I've listed here, the Hi-Fi 1 new port that is available. And it's all part of the SDK. So when you download Zephyr SDK, they have a bunch of architectures available, like ARC, x86, ARM, and RISC-V is one of them, RISC-V 32-bit. So the SDK has all the support, courtesy to all the tool chain work and everything that happened. FreeRTOS. It's very recently. I read the blogs from the AWS guys, where they declared that they have now RISC-V support for FreeRTOS, which is a great news. It's currently supporting, as per their article, both 32-bit and 64-bit instruction sets. So, but of course, it's just the soft float profile. So primarily, that covers our kernel pieces. And then I'll move on to the next, which is more Linux distribution support, which is now putting the whole operating system together. And we talked about this earlier, that desktop distributions, they have agreed upon a common ISA, or the with extension that will be used, and that is RV64GC and 64-bit ABI. That is for RV64. Maybe in future there will be RV32 port, I don't know. But so far its focus is only on 64-bit port. And Little Endian is the default NDNS for the common Linux operating systems. Embedded Linux story is a bit different though, where you can have all these variants of CPUs where a standard distribution might not be sufficient. So you might have to have embedded specific distribution, and we'll cover those as we cover the distributions. And I think there is a talk in the afternoon where we will cover actually embedded Linux in much more detail. So you'll probably have much deeper insights into it. I'll go over the other distributions as well, in general. So you might have custom extensions, for example. If you have all those, you would do those using those. Embedded Linux distributions will provide you infrastructure to do that kind of stuff. So Fedora is actually very active in doing the RISC-V work, and in fact it's in a very good shape right now. So there is a wiki where they describe actually in a really good description. If you are Fedora users, go try it out. They have images that are now available for emulators, so you can basically get it up on QEMU. And all the packages I saw are on, so it's now being actually added to the Koji build form, which is their standard build form. And the bootstrapping images are already available. So I think at this point it's in a fairly good shape as an architecture. And they support the Hi-Fi Unleashed board, which is actually one Linux-ready board that's out there. And then the QEMU, of course, which is another board that is supported. Debian also has actually very active community working on RISC-V. So I always like this graph from Debian, which lists how many packages are being basically ported. And as you can see, RISC-V is way above IA64, for example. So it's fairly large number of packages now in Debian that are now buildable on RISC-V, and it's always going up and up, and I think sooner it will be in the same league of x86 and ARM. So it's a good measure of how the porting work is happening. SUSE. So OpenSUSE, they have at a similar level, they have pre-built images that are available for you, and if you use Tumbleweed, you can just install Tumbleweed on one of the hi-fi boards or QEMU and use it. So if you do any kind of application level work on porting any specific software, I think right now maybe a distro of your choice is already working on RISC-V, so go ahead, try it out. So Yocto project, OpenEmbedded. So primarily, I covered few of the main desktop distributions, but there are a lot more that have ports either available in works, and I think if you go to, there is a software status page on GitHub for RISC-V, and that's a live document. So whenever something is being added, being upstreamed, all those status is reflected on there. So for more accurate information, or if you use a particular software that I didn't cover here, it will be probably there, and it will reflect the current state of that particular package or a major infrastructure. So I encourage you, go there and check for the things you are interested in and what state they are in. OpenEmbedded and Yocto, so this was actually one of the first embedded Linux distros that was used at UC Berkeley to port, basically to bootstrap the architecture. So there was actually a fork called Pokey RISC-V that was used to do all the work, but they never upstreamed all that work into OpenEmbedded. So it has diverged quite a bit for a while, and it was based on a very old fork. And so what we did later on, so I also contribute to OpenEmbedded project, and we basically upstreamed a lot of the base support into our core layers, and then we created a architecture layer which is hosted on, again, RISC-V GitHub handle, and it basically interacts with upstream layers, and you can build actually for a lot of boards actually, including emulator, 32-bit, as well as muscle, glibc, all those options. That is what OpenEmbedded gives you. You can pick and choose. You can put together your distribution the way you like, and you can also put together SDKs for other like bare metal work and all those things, because I talked about Zephyr. Zephyr's SDKs are actually generated using OpenEmbedded. So you could use OpenEmbedded just not for as a distro, but you can also use it as a infrastructure to generate your tool chains to do your embedded work, or if you are doing some FPGA work where you are using it in a microcontroller, but not a full Linux distribution. So this can help you to put together all the tooling that you would require. So I think more there is in the talk in the afternoon, where this one slide probably will be discussed in a lot bigger sense. So we now have recently we were using the BBL as our bootstrapper. That has moved away. So OpenSBI is what we use in OpenEmbedded now. So it's actually at the moment one of the leading distributions for RISC-V to get to implement various pieces, and I think it's on the latest and greatest kernel, and thanks to Western Digital for a lot of those contributions. And emulator is also in a very good shape, and they have also contributed the OpenSBI contributions came all from them, and 32-bit actually, RV32-bit also came from from them. The way it is set today is actually where I talked about scalability of architecture. It really goes in here. So we currently only support like the base common ISA variants, but you can easily enhance it to say you implemented a chip where you implemented a double floating point, you can, or you eliminated it, you can easily represent that in OpenEmbedded and generate your own distro. So I think that in future this will go hand in hand when RISC-V really scales up. It's a good distribution to go with that philosophy. Yeah, so I think we've been always targeting it. One of the, I think the entry points for currently in OpenEmbedded is testing. So for it to get into, so right now, don't get me wrong, like, you know, most of, if you look into Meta RISC-V, it's very light layer. We don't have much things in there. It's only BSP definitions and, you know, a few other things and few patches that we carry for certain packages. But as we move into future, I think one of the acceptance criteria for getting into core would be the p-test framework, and that still doesn't work. I think it doesn't work. I think it's a small problem that we need to fix, but the hope is that in coming releases, probably this year, we should, if we fix this problem, then I think it makes a fairly good chance to basically get our QEMU machines into core. And so I think that is what we're gonna kind of, I was talking offline here as well, that, you know, that's probably a priority for us to get fixed and then start basically pushing it for the next release, provided we can fix those issues. They are still at large. Buildroot also got the support, and so actually if you're a Buildroot user, Buildroot have both 32-bit and 64-bit ports since December, and I think 32-bit port was added immediately after there. So right now, so I think the RISC-V start was the branch that was used before, but right now you can just use their upstream master branch and you can build for the emulator as a target. So MB Cosm was actually the contributor for that work primarily. So so that's primarily like a high level what has been done so far and is available upstream for you. And then I think I'll go over some things that are around ongoing work. So if you go to like RISC-V handle on GitHub, you will find there are several forks of the project that are still there. It's a temporary staging area for, you know, the RISC-V community to host those repositories and do the ports, and then the idea being that it will be upstreamed, and eventually those repositories shouldn't exist. So what you would see is that all those ports will get upstreamed, and like it has happened for other projects. So you will still see that there are several projects that are hosted there and that are still being worked on. LLVM port is actually available in 8.0. You can actually, Clang is also available as an experimental port. So you can build it and use it. I've tried to. It's not in a production stage or anything, but it's usable. You can build, you can generate like smaller examples. It's progressing in the right direction. Missile C library, we talked about it a little bit. The patches has been done last year, and they've gone through a few rounds of reviews, and for lack of time, sometimes the reviews hasn't been addressed completely. And so I think there is another review cycle happening as we are here, and I think most of the 64-bit port is actually in has kind of all the reviews addressed. So hopefully maintainers would accept it in coming weeks. What that gives us is that now there are certain distributions like OpenWRT, which uses Muscle as their C library, and Alpine Linux, for example. The most widely used distribution in the Docker world. They use Muscle as their standard C library. So it opens up the way for those distributions to be upstreamed. So Alpine actually already has taken these patches actually and vetted them against I think one of the developers, I don't know, they have their own fork that they reported and blogged about it, saying that they have the basic port for Alpine working on RISC-V, which is a great news. OpenWRT also has a port that's available, and they also publish the feeds. They are not upstream yet, but they are in a staging area on the way upstream. So that's happening. But if you dabble with those projects, I think these are the areas you would look into, and you can kind of like get in and spend your time if you are participating in those communities. Golang actually is there's a port that exists on a fork on RISC-V on GitHub handle. It doesn't have all the features for Go. For example, CGO is not there yet, I think, and it's not upstream as well yet. So I don't know what the upstreaming plan is there, but I'm pretty sure that there is some. And I haven't played with RISC-V Go yet myself, so don't have much details into in what shape it is to tell you. But in the past, I think it has been there. Being used on some distributions already, so I assume that it's in a usable state in the fork. OpenJDK doesn't, it's a very basic support that's in there. There's no hotspot support and all those things. V8 engine, there is nothing that has been done so far. Node.js is in the same boat. So I think the larger ecosystems, the bigger ecosystems are still not yet fully done. So maybe there is if you are help needed quite a bit in those areas. If you work in those communities, feel free to participate and get RISC-V as a first-class citizen in there. So hardware-wise, I think talking about like full Linux hosted Linux distributions, there is Sci-5 Freedom board, which is kind of a bit expensive right now. On this, it's like under $1,000, but it's actually a fairly good, like 4-core CPU, and you can basically do a lot of native stuff on this one. So hopefully there will be new boards which are affordable coming out, like in a Raspberry Pi factor. Hopefully, I don't know. That's my wish. But if that happens, I think that will be really good for the community. What I see is that without all those, so much has happened on the architecture, porting all large pieces of software. I think this will just take it to the next level. But it's a matter of when it is going to happen. Somebody will come up with a board which is affordable. I'm pretty sure. The way, yeah. Yes. So you can go, especially on Sci-Fi's GitHub handle. They have published several schematics in there. So I think they keep publishing every now and then as well. So I don't know what the current state is, but they have several open, reference implementations that they're published. Yeah, it's a bit complex.
So So there are definitely dedicated cores you can get, but I don't know where the line is. There's some line, like the cheaper one.
Yeah, where's the line?
It depends on the configuration. But there's a lot of open.
Because I thought of implementing alpha architecture on a cheap FPGA. It doesn't have to run fast, it just has to be
Yes.
a verifiable architecture. This is actually really exciting. You know, there's a RTL with Verilog. I'm not seeing how small of an Intel gate array will fit on.
Yeah, there's a few. There's Boom, and Swerve, Flat5, all have open. I think Rocket.
Cool.
Yeah, so I think there are certain tries in that area that people are doing, and I think it's an area that probably you can.
It's really amazing to me that the gate manufacturers of these devices will sell you an FPGA evaluation kit for a fraction of the price than if you bought the part itself and put it into a product.
Mm-hmm.
So they really want us to implement stuff on these evaluation kits.
Mm-hmm.
And that's really exciting for us.
Yeah, yeah. Yeah, so I think definitely more, you know, if you dig more into it, probably it's doable, I think so, but probably no one has tried it yet, given that, you know, the complexity you need for the chip for running a full Linux kind of with all virtual memory and stuff. I don't know. Maybe it's doable.
Company called
Macrosemi, yeah.
That's one they announced, or is it? It was announced in early summer. Yeah, that's what I think. That's how you. Oh, that'll be a hard talk. With FPGA fabric. Okay. But it's not hard.
Yeah.
This is going to be really exciting because you realize it costs a considerable amount of money, $30 million, to be able to change the ARM architecture and add on to the ARM. So companies that want to add like security instructions, that's not big, stuff like that, you've got to be willing to put up $30+ million. That's just a guess. Before the ARM will let you actually extend the architecture.
Yeah, I think that's. I'm not privy into like all this licensing and stuff, but you might be right. Like, you know, in the ballpoint figures, it depends who the, you know, the other guy is, and you know they have all those contracts, but it is expensive.
So this is an opportunity for us to really, as an industry,
Yeah.
really do amazing things.
Yes. So that's why, you know, it caught my attention and my kind of imagination that, you know, what it can do is amazing. In this given, you know, AI of things world, right? Where everything is a compute which is not same as others. So general compute is kind of lived its way. It's good in data centers, right? But as AI becomes more and more common, your compute units are very unique. So, you know, you cannot do everything in software, for example, right? So the philosophy that we had for so long was, you know, let's create hefty computers, put them in cloud, get the data, process it there. It can only get us so far. So it has a fairly, I mean, it's coming up in a right time, I would say, and interesting times. So I think there is more information that I've covered here. There is a software status, as I was mentioning. It's a live document. You can always go in there and look for. And as people announce different SoCs that they're developing, they get added there too. So, you know, that list is growing. It used to be 4, and now I see it's like 20. So that's a good progress. And then there is a separate kernel mailing list if you're interested in kernel. Then there are several other mailing lists that are available here that if you want to get involved. But the philosophy is that everything is upstream, so you really don't have to interact with the communities to accept patches. You can fix a package and send it to that upstream wherever it is. So you really don't have to kind of get through RISC-V and then upstream it. It doesn't matter. So most of it will be upstream. If it is not, fix it, send it upstream. So that's as simple as that. And there is actually IRC handles too. So there is a RISC-V channel on Freenode, a lot of folks hang out there, so you can go ask questions or just listen to what people are talking about, various things. So it's a pretty informative channel. People talk about a lot of interesting stuff. Stack Overflow also has a tag, so you can go in. People are asking questions about RISC-V in on Stack Overflow. You can go answer, participate, provide your feedback. So I think that kind of spreads the knowledge to people who are trying to use it. So so I think it's also getting a lot of press coverage that I've seen in past few months, and in fact late last year, where people are now looking at it, what it means. Is it too open, or is it not that open? So they are doing comparisons, right? How the processor industry has been doing and what it can get us. And so interesting articles out there, and I read this article about too open to fail, right? And they talk about what you were alluding to, is licensing and all those kind of things. And at the very end, it's interesting, the author said that the next article will be too open to succeed, right? So so that'll be interesting read to move forward. And I see it being covered on a lot of other places, on Hacker News and other places. So there is a lot of good stuff that's happening around RISC-V, and I'm excited about that. So I think I always compare it with this analogy. So if you recognize, this is an email from Linus Torvald, where he announced Linux. I've written a kernel, right, and it works on i386, and go have fun at it, right? That was in 1991, and today we know Linux is everywhere. And one thing that it's been common here is that it was open source. So as we know that history tends to repeat, and maybe this time it is for a processor, who knows? Time will tell, but it's an interesting time. And I think what I see is, I was talking to a few folks, and they were saying that the number of startups who are doing hardware has gone up in the recent past, like 1 year. Given that the architectures were getting so less in number, that people have been innovating on software so long, that hardware innovation cycle is returning, and there is several people who are trying to do like a lot of stuff using RISC-V and maybe other architectures too. But certainly I think RISC-V is contributing to that wave, and I'm just hoping that this will turn out to be something really interesting for us in future. And 20 years from now, maybe this will be one of the architectures to reckon with, and it will be basically dealing with our all AI and machine learning loads, which require this specific compute that is not general in nature. So I think there is a directions towards that. NVIDIA has announced their cores, for example, which is RISC-V based. I think one of the open cores that they've announced. So I think there are others who are now also working in those directions. Like there are, like TPUs are a typical example that there is a requirement in this industry, or like car industry is trying to do the visual compute and all those kind of things. Those are special kind of loads where you can't put in a server class CPU into your car and with the fans and then do that kind of compute in there. So you need like specific compute modules, and I think this is a good core that somebody can pick and say, I have an idea to implement a neural network, and then I have an ISA. I don't have to license it from anyone. I can just go download the spec, design my hardware. So I think one of the things that would be the tools that other, especially EDA tools that people use for designing. I'm not sure that those are as good as others yet, but I think Sci-Fi has done some of this chisel stuff, which sounds pretty interesting, where they're trying to do a high-level design using, SCaLE, I think, so, which is a very different approach for doing the design. But I'm hoping that, the tooling around the hardware will come up and will be pretty modern. So, instead of how we do software today, right? We do and we redo. You could do hardware too. It doesn't have to be that difficult. Probably you can design it, redesign it, and the cycles will be smaller. So today we don't think about software. Okay, there's a bug, we can fix it, right? But in hardware, it's a big thing. It's a very big expense because of all the verifications we do. So the reasons some veteran at Intel told me is that in some cases they do a local optimizations on assembly in Verilog. And so they cannot recompile the whole thing because that tweak goes away, right? So most of it is very manual for them. So verification is very, very long for them. So you need high-level tools, right, for all this to speed up. So I think there is something happening in those areas as well that people are doing. So I'm hoping that this will be a tool for people to try out hardware innovation again. So I think that's what I had for today. And so I think if you have questions, we can discuss those. And thank you.
Great presentation.
Thank you. Yeah. So there is a rep from Western Digital here. I'll let him answer. Do you have the Hi-Fi board, the Freedom U, the Freedom U540 board as well, or yes? So yeah, so there's the SBC from Sci-Fi, which is not cheap. It's like $1,000, something like that. But yeah, so. So Raspberry Pi Foundation joined RISC-V Foundation recently.
Really?
Yes. So I would not read too much into it, but I'm hopeful that they probably would come up with a design probably in future. That is, maybe there will be two different kind of Raspberry Pis. I don't know. Sci-Fi is the company. The board name is Hi-Fi. Yeah. So I think there are some like microcontroller boards that are already out there that you can get fairly easily, and they are under $100, $50, but they are microcontroller boards. So for full Linux distribution level work, you would either use QEMU, or you would have to get that $1,000 board. Yeah. So that I think is also shipping in market right now. I think there are a few products which are already shipping RISC-V into market in that place. Yeah.
Yeah, a couple things. One, I know some Linux conference, but I'm sure like FreeBSD runs on RISC-V kind of, historically. Also, I was wondering, like Western Digital has things that they're building out of it. Is they're like focused on trying to start with dumber devices that are easier to implement, a chip for, like, network card, storage controller, whatever, to kind of work their way up towards the general
compute.
Yeah.
Yeah, I think so. I mean, this is my take on it. Like, unless you do a native build, like, you have a system that you can give to a developer where he says, okay, I do native work, the software systems is not going to ignite so much, right? So RISC-V has to have that full system to a certain extent. Maybe it is not very cheap, and it can't get to that level for whatever reasons, right? But unless we reach that point, it will be like, it will remain a little bit, this will be a problem for developer community. So I think it does have a value to have that kind of system, that will be there. But I think, yeah, network cards, definitely I think that is a use case that people are actually exploring as of today. I think that's more practical from product's point of view. Cheaper, yeah.
You had mentioned earlier in the talk that you said that the user space of RISC-V has been monolized. Does that mean that there's, to make an analogy to x86, there's some sort of microcode going on underneath, something like that? Or what did you mean exactly by the user space of RISC-V?
So what I mean by that is that the APIs that you would generally use for design, right? So all the implementations that has been finalized. So the specs has been versioned, right? So we implement version 2.0 of user spec. So the instruction sets, they are known, right?
Almost like the POSIX C standard.
Yes.
You're going to have like a POSIX standard.
Correct.
Similar to RISC-V.
Yeah. So you want to implement an instruction set, right? And then what those instructions do, right, is in the standard. So you implement that. So basically, if everybody was implementing 2.0, right, then they are compatible with each other. That is what. No.
Yeah, you have to like work your way up from the microcode to the assembly language to the high-level language, whatever.
Yeah.
Well, well, the question, I guess, that makes another question is, because of how new this ISA is, are they coming up with instructions that are running at shorter time intervals? The whole reason why Intel and all the big companies have microcode is because we've gotten so much faster with our clock rate, so that they can now do things while they're waiting for I/O and things like that. Has the design of this ISA kind of shortened that, like we don't have to rely on microcode as much?
Yeah, because everybody did that before, right? So they had prior art. So it's not that they came in and they shut their eyes off and they said, well, let's do something new. For example, they took best practices from previous architectures, right? Like a typical example is like the 0 register from MIPS, right? That makes your instruction smaller, right? So they took that design and implemented it in the specs here. So likewise, there are other things that they have learned. So the hope is that the ISA that they will come up with is basically better than what we have done in the past, right? We always will have future, and I will not shut it down for future that, okay, this is what it is, you cannot improve it, right? They might be. But what it gives you is a common kind of a scalable set that you can start off. And it doesn't either enforce you like, with ARM we went like totally different ABIs completely, right? So they were not like each other. Or it is like the other way, you look at x86, where everything has to run on, x86 at a lowest common denominator, right? So it's somewhere a kind of a balanced approach for the design, primarily giving you a common set to begin with, and then scale it up, and then have the building blocks that you can put together to build a logic. So. Mm-hmm.
Expect on a processor. And there you have a verifiable processor that you are certain how it behaves. For IoT control and stuff like
Mm-hmm.
that. Now you don't have to worry about meltdown inspector and a whole class of things that we all talk about every day.
Yes.
Well, what if?
Yeah, that's what it's something you can audit. So you can say you can look at the spec and you can run the processor and you can verify it's all of the spec. There's no secret. There's no black box you can't see inside.
Right. Yeah, so I think that's one advantage. So like there is a memory model is verifiable. It's put out there. somebody can write an emulator or simulator for that and verify it. And obviously, if there is a glitch that is found, we'll fix it quickly because we all know there is a problem. Rather than, so, that security by obscurity won't be there. And obviously, there will be holes, right? We will never, we can expect a architecture to be 100% foolproof because it is open, right? But just the process will be different to fix it. Yeah.
So, somebody could run tests or benchmarks against Zephyr, say,
Mm-hmm.
compare to Cortex maybe doing anything like that?
Yeah. So I think I'm not sure whether they have published it, but Sci5 does have benchmarks against their I forgot the name of that board. Hi5D, yes. Hi5 which is a microcontroller against Cortex M0, and they claim that they are a lot better in terms of power. Lot means lot.
But that's part of having, like we talked about, having to have the tooling. If you're going to run the test, you got to compile something to run the test. So then you have to have LLM, you have to claim or something to compile the tool and run the test.
Well, I said to this.
Yeah.
Seven.
Right.
And there is this process that when you take something from, let's say, emulation to an FPGA, you don't really have the capabilities of optimization as you like. In one project, when we went from the FPGA to Verilog, we had throw away 90% of all the enhancements we did in the FPGA so we could run this sort of not a process for it. And when it goes to Verilog, it's optimized by whatever tools change you have. Now the difference in performance might be 1,000 to 1. I mean, it's hard to say. I can't say what it is, but it's going to be an enormous difference between the performance of an A6 and an FPGA.
Right. So yeah, I think there are. I mean, the version 1 of the U540 board, which is Linux capable, wouldn't be a fair comparison as of now, because I would expect the V2 to come out, where I think then you will start to see real-world benchmark like Phronix or something that you can start doing that kind of stuff. So.
That's a good thing with Western Digital stuff. They're going to put on a board. Now you can attach that to a spindle and see what happens.
Right, then you can run storage benchmark.
Right.
Yeah.
That's super awesome. Particularly if they use something like FreeRTOS or something like that.
Now I'm always kind of like a learner go get them, then we'll school them.
Yeah, so I think it opens up an opportunity for people who are new designers, right? The young kids, for example. I'm excited about those people. Especially I see, I think India has invested into it, $42 million as their national architecture, right? So they are basically designing this into their school curriculums and university curriculums. China has a lot of projects already in there. So I think the reason is because it's open, it basically will be a lot more chance for people to try it out. And so I think if it stands the test of time, it will be the architecture to reckon with. So cool. Yes.
What license is it under?
BSD.
Yeah, Berkeley made it, so.
Yeah, it's from Berkeley, so what do you expect?
So does that mean that if you take the source code and spin a private chip,
Yeah, so in theory, a certain company could be well known for making faster RISC-V chips because of they could implement their own microcode. In theory,
Yes.
that has a
Permanent knowledge and then a company to use it, right? No GPL, no overtime.
Right, well, the thing is, BSD, it gives you the lowest common denominator. It's please use this, it's going to be at least this good. Don't try to reinvent it. There's a lot of talk.
Yes. It's commoditization. Basically, this is what is required, right, in general. Otherwise, you do a lot of duplication, which is not required.
It's basically when you get really hard technical problems, BSD license is kind of good because then, like I said, it gives you a lowest common denominator.
Yeah.
But a lot of people put a lot of mind into figuring this thing out. It's a long time to come up with.
Yeah.
You can try to reinvent it and knock yourself out, but you're probably not going to do better than this to start with.
Yeah.
You have a proprietary version of something that is best known for being open.
Well, yes and no, but the part that's free
talk about this, and the consensus is don't take that risk because it's not arguable. And then Linus goes and says, well, maybe it is. And that kind of defeated all the hope that the drivers would be forced to be open source.
So,
Like TCP/IP was BSD license
yeah.
implementation. And the lowest common denominator, how to send packets across the internet, how to route them, how to schedule them, all that stuff.
Yeah. So I think.
I don't know that history, but the point is if you're China and you're interested in this, because you can ascertain that there's no NSA spyware in there, it's now closed again.
Well, yes and no, but when you want to go into that, then risk 5 is better because
You know the daemon that you're beginning with.
you don't, because what if you bug the chip that you build the compiler against, and then you audit the compiler and it looks perfect? So what? You still can't see the ghost in the machine.
Yeah. It's.
You can go lower than lower than lower than lower than lower, you're never going to see it. You always have to trust, there's always a way in.
But even if you put the chip in a machine, the technology, let's say it does have some cool backdoor.
Right.
I've been there, seen that.
Yep.
The chip has to have the opportunity to use that backdoor.
Mm-hmm.
And so let's take a storage controller, which I got a lot of. Well, gee whiz, there isn't much opportunity there. People talk about hacking chips, which is a serious possibility.
So backdoor could be vaporware too, is what he's saying.
Yeah, it's okay. It used to be we cap the chips and look at them under a microscope on systems. Make sure that what you have built is what you got. Right. But when they're moved to making things commercial that are our government pushed under the radar, no one could afford to do this.
So China can hack GPL stuff too.
This is far superior because if you implement it straight up without huge amount of optimization, you got verifiable.
Yeah.
You could run SD4 on it, which I'm not a fan of, but you could, and then you can say that your operating system and the chip is all verifiable.
Yep. Yeah.
And that's the big trick for that right now. They have like reproducible code.
Mm-hmm.
So like you download something from FreeRTOS.org, you build it, you get exactly the same checksum as the ISO told you you would get.
Yeah.
No matter where you build it. So you can do the same thing with the ISA.
Mm-hmm.
Make it reproducible.
Yes. Yes. I think that's big. But the capability is there now. You could do it.
Yeah, you could do it before because Intel won't tell you enough about it for you to verify it properly.
Yeah. We did.
Or there's too much secret sauce.
Yeah.
Isn't about to do that either.
Yeah.
You pay for those designs from ARM. And you do not change them. Right.
All right. Thank you. I think we. Thank you.
Good discussion too at the end. I think that was fascinating. 1, 2, 3, 4. That's better? Okay, good. Okay. I'll leave this here in case I have to move things. Okay, welcome to this afternoon session of the embedded track. We're going to be talking about FPGAs. How many here have heard of an FPGA? How many have used an FPGA? Ooh, that's good. Good number of people. Okay, great. All right, in this talk, we're going to not give you the complete nuts and bolts of it, but we are going to be talking about some of the exciting new developments, which are open source tools to actually be used on FPGAs, which means that instead of having to download 5 gigabytes of stuff for one particular thing, you can download and build the tools yourself, and they're a lot smaller. So that'll be fun. All right. Initially, this talk was going to be given by Merrick. He had trouble getting a visa because the embassy was slow in Prague this year, and so he was not able to come, and he asked me to give this talk. Although I've seen him give this talk before, so I knew it, at least know it. And I've also been working with this as well. So thank you to Merrick for making this talk available. So basically, we're going to talk about these 5 things. We're going to talk about what it is, what type of design tools there are and what languages are available. We'll take a look at a small design, talk about debugging a design, a little bit about debugging a design, and the conclusion. His lab did not work for me, so I had to come up with my own, and I was working with a friend of mine in Phoenix who has built an interesting project on a very inexpensive board. So we'll start with that. Okay, FPGA stands for Field Programmable Gate Array. It's a programmable device that you can multiple times program it because it generally has an external PROM to actually program it. It's all logic. There's no real CPU in it or anything. There's no real programming for it. You have to decide to build up all the little blocks for it and to whatever you want it to do. A lot of them have a minimum of, let's say, 100 IOs. So they got tons of IO space available. They're not really all that fast when you compare it to like a CPU, a modern CPU that you have, but they give you plenty of options for IO. Some of the more modern ones have endpoints for things like PCIe or for gigabit Ethernet, so those are all available. Extremely parallel. If you're used to programming, things mostly go down 1, 2, maybe 3, 4 threads. In this, you may have thousands of things all acting at the same clock cycle. Every time another clock cycle happens, a whole bunch of things happen in parallel. So you have to think differently when you're programming an FPGA. They're used a lot in DSP, and digital signal processing. And that's because one of the things that they do really well is they do things repeatedly over and over and over and over again very rapidly because they can do things in parallel. Parallel data processing, if you've ever done anything that requires a bunch of parallel processing. Let's say you have a custom hardware interface that's different than somebody else's standard. Let's say you have a camera for whatever reason that has 27 bits coming out of it. And FPGA is what you do to capture that data and then pass it on to your computer to be processed. ASICs. Anybody heard of an ASIC? Seen an ASIC? How expensive are they? Okay, millions, that's correct. So because ASICs are very expensive, and oh, by the way, if you do a spin once, that's $1 million. Oops, I did it wrong in the silicon. Oh, that's another $1 million. So rather than do that, we'll actually use an FPGA to do the prototyping. What other uses do you know of for an FPGA? Anybody else who's used anything here?
High-speed analog.
High-speed what?
Analog.
Absolutely. High-speed, and like I said, camera capture and stuff like that. How about this? Let's say you've got a part that was made in the 80s. The manufacturer no longer makes it. But you happen to have a contract for a government or a military that says, oops, we need you to replace this because we still got this system that we're using and we can't get these parts anymore. By knowing the data sheets, you can actually build it in an FPGA.
So like emulating Spark or something?
We'll talk about that. You could emulate Spark in that, as long as you knew the internals of it, yes. Okay, here are some of our common vendors. Common vendors are Xilinx and Altera, which is now Intel. Lattice, which we'll be talking about today. Microsemi, those are some of the normal ones that you'll see out there in the field. A lot of these guys have been around for a long time. All right, this is kind of what they look like. I say kind of because every one of them's got its own internal architecture and they're all slightly different. Okay? Within each FPGA there are logic elements, and you can see within the logic elements there's a logical device and the register, the LUT as they call them. They also have global interconnect that connects them across this thing. They call it fabric. That's the typical term for it is fabric. And it kind of looks like a fabric because it's all interwoven together. They have the blue, which is global interconnect, the green, which allows you to connect locally within that piece of the fabric. And then they have a logic elements, all these different logic elements that are inside of the fabric. Additionally, which is not shown on this, are things such as local clocks and global clocks. So with these logical elements, mostly turns out to be close to flip-flops, you can actually create most of the things that you need in an architecture. AND gates, OR gates, all the other different pieces that you need. Any questions about this before I move on? All right. So what things are available? Like I said, I wasn't going to do a deep dive into how an FPGA is built because every one of them is a little bit different and everyone's done as a proprietary thing by whoever the vendor is. And all their data sheets show their architecture and how it's done. So Altera and Intel, the ones that people don't normally see, thank you for telling me that. Cyclone 4, 5, the 10 versions, Max 10. Anybody ever played with the hybrids, where they have a couple of hardcore ARMs in them, and then they also have FPGA fabric? That's another thing that's becoming very popular, especially in the Linux community. They're using Linux to run in the hardcores, and in the soft cores, they're doing whatever special thing that you need. Today, we're going to be talking about Lattice with 2 T's, and the product we're specifically interested in is the ICE40. And the reason why we're going to talk about the ICE40 is because that's where they started with the open source tool chain that we're going to be talking about today, specifically. Then there's Microsemi with their PolarFire and other products. The Spartan, Arctic, and Zinc, which is a hybrid, right here, the Zinc is. And when I say the word hybrid, I mean it has hard cores and soft cores in it. So you have hard cores of ARM processors specifically, and in addition to it, you also have FPGA fabric available. So both of those are available on one die, and brought out to balls on the FPGA itself. Any questions? All right. There are other vendors. These are probably the big 4 that you'll see in most projects. All right. Now we're going to start going into the tools. Each one of these vendors has their own proprietary tool. Intel has Quartus, Xilinx has Vivado and ISE and a whole bunch. They're proprietary, they're closed source, and they are enormous. I just recently downloaded Vivado and it was 15 gigabytes. Now, that's for every one of their pieces. And it also includes some locked up things like some IP that they'll sell you and what have you, but that's all locked up unless you get a license code. So you see a lot of big things if you have to do it. It's a big learning curve, and oftentimes it requires a fairly substantial machine to actually run it. And part of it is because they've got a lot of optimization for these big FPGAs built into it. You know, the ones that cost $1,000 a pop. If you blow it up, that's not good. So we're going to talk mostly about the open source tools for using it. We're going to specifically talk about one specifically for the ICE40. ICE40 uses these tools, IceStorm, Next PNR. PNR meaning place and route. That's how you actually tell it which logical elements and how you're going to interconnect it. That's what the place and route does. The Lattice ECP5 using the Trellis tool. Zinc 7000, there's a project called X-Ray, and then Altera's original Cyclone 1 is Chibi. And these are all tools that have been developed by open source people to deal with the problem of how do I take these relatively inexpensive FPGAs and FPGA boards that are coming out and actually use a tool which I understand what it's doing, or at least is open source, if that's important to you. These tools here, like Chibi, X-Ray, Trellis, and IceStorm, all are efforts at reverse engineering the fabric of whatever device that they're looking at. So for example, the ICE40 probably has the most work been done on it. A guy named Clifford in Austria, and he has reverse engineered most of the elements of it. Any questions about any of this so far? Okay. All right. Yes, go ahead.
Of these different platforms, aren't there some that have enough vendor support that we don't have to do any reverse engineering?
Define vendor support.
Vendor support for open source development.
No. None of them.
Still none of them.
None of them that I've seen. They started with the Lattice ICE40 because they were inexpensive and they had a lot of stuff on them. This was actually done as a university project, like a lot of other things get done. It was started as a university project.
So we're still developing off the reservation if we want to use open source.
Absolutely. Absolutely. We're not there. We're definitely not there yet. Yes?
Some of the proprietary tools are free to a point.
Correct.
Use them to,
Yep. Yep. We're at an open source conference here, and a lot of the people I know would rather not use somebody's proprietary tool in order to do whatever they want to work in. This is part of the reason why we're doing this. The other reason why we're trying to do this is because closed proprietary tools, that as soon as you get to that certain point where you hit that point, you can't use those IP blocks that are for the higher end parts. So for example, the PCIe block or the high-speed serial ports that are available on some of these larger FPGAs, even the ones that cost $20 or $30, they have some of those hard points on there. You can't get them unless you buy a $500 or $700 part license. Not just, you have to have the license for the tool, and then you have to have the license for the IP block that runs that. So those are the kinds of things that they're working towards. All right. So the ICE40 came out, some of the original ones, the HX and some of the other versions, and they started to be reverse engineered. Other people jumped on and said, oh, I understand this process. It's a tedious process, by the way. You put in some code using the proprietary, you see what comes out. You try and emulate it with yours and say, oh yeah, I got it to do the same thing. It's a very slow process to reverse engineer this.
Question.
Yes.
If we're relatively new to developing on FPGAs,
Yes.
are we making our lives much harder to try to do this with open source tools?
It depends on the hardware you're using.
How so?
If it's any of these, this is probably the most mature, right here. The further you go down this, the less mature the tools are. It's not that the tools are, but the less mature the definitions are. They haven't had a chance to find certain blocks. I'll put up a link to the SymbiFlow talk that was given at LCA this year, the LinuxConf AU, in which they talk about the state of where things are. I saw that talk when I was down at LCA, and It was a very good talk. Unfortunately, the only thing I have, wasn't able to get the slides. I've only got a YouTube video, and it's kind of a pain, and it's a long talk too. But he was talking about the state of where things are. Certainly the Lattice ICE40s are probably the most mature in terms of being able to use them. However, other ones are starting to gain speed as people say, hey, I would like to use a Spartan 7, or I'd like to use an Arctic 7. People are starting to work very much on trying to make that happen. Okay. All right. The flow is pretty much similar depending on whether, it doesn't really matter whether you use the proprietary tools or you use the open source tools. They all have the same basic workflow. They take HDL. HDL stands for Hardware Description Language. There are 5 or 6 of them that are available. System C, Verilog, VHDL are the more popular ones. There's some other additional ones that are coming out as well. Those hardware description languages give you a net list. If you're familiar with EDA tools, you know a net list is how do we wire all this stuff up. That's what it's for. From that, we take the net list and we place and route it. Remember I showed you the fabric. If you take a look at this fabric, we have to place and route what element am I going to use and how am I going to connect it up through this fabric. All right. From there, we go to the technology. The technology is that reverse engineering bit that's going on today. That's the how do I, if I tell it this thing and I put this piece of information in, what does it do inside the FPGA and what do you get out of it? That's kind of the next piece. And then once you get done with doing the place and route, then you have to create a bit stream. A bit stream is the actual programmed instructions to tell the FPGA how to hook things up. And that goes into your PROM. They're almost always some kind of a serial PROM. They also have parallel ones for the higher end devices to get them to load faster. Most of them are get loaded over SPI. So you can actually, if you want to, you can jam directly in over SPI and avoid using a PROM. But of course that means when you turn it off, you have to reprogram it again every single time you change the hardware. I'm sorry, every single time you unplug it and plug it back in again. Additionally, there's analysis tools for timing. Remember, we're talking about defining hardware. So we're going to define all of the clock signals and make sure that the next memory cycle that you're going to have inside the device is all lined up with everything else. All that analysis on the design, checking to make sure that your timing constraints so that things aren't skewed or off, and so your memory doesn't actually get accessed at the correct time. And then eventually we also have simulation and visualization tools, and those have been around for a long time. If you've ever used GTK Wave or some of the other things, those are available. And then we're just taking the output of the Verilog and turning those into a waveform that can be seen. Pretty much what we're going to talk about here. Any questions on any of this? Okay. All right. When we write HDL, we get output and go through the tool, which is a Verilog, usually a Verilog or VHDL compiler. You'll get a net list out of it. That net list again is the list of how you hook up the different pieces logically. This is ANDs and OR gates and flip-flops and memory and how RAM looks like. All of that is a hardware description. There's also a behavioral model that you can use. Let's say you know what it's supposed to look like, combinatorial logic. You have ANDs and ORs all put together. That can create an actual schematic. So it's not unusual to see you go from HDL, this hardware description, and the output is a schematic that you could actually look at and say, oh yeah, that's exactly the way that I wanted to make it run. That's exactly what I want it to look like. The analysis tools are trying to parse the hardware description language, all of this circuit, how it's supposed to look, and then validate it for timing. Typically, it's validated for timing, because remember we were talking about in a parallel universe, because That's what an FPGA really does, is a lot of things at the same time in parallel in different pieces of the FPGA. These pieces here all look the same, mostly look the same. You'll notice that this, and this is repeated over hundreds if not thousands of these blocks that are inside of it. But you program them as to what the actual gates are going to look like inside and how they're going to be used. And one block in one section may be completely differently programmed than another block in another section, but they're all using a same common clock. So when the clock ticks over, the next thing happens in every one of the blocks that use that clock. All right. And this. All right. One more. Okay. And then eventually we take and synthesize it. Much like programming, we have to much like the GCC, where GCC will take and run, first of all, it'll run the C++ parser, which will then go to C, which will then go to object, then be assembled, and then eventually get us linked together and put out into your project. Same thing with this. It goes through different pieces in order to do that, and eventually we're going to end up with being able to do the place and route. After it synthesizes it down to a net list, then it'll figure out how am I going to efficiently use the logical blocks and interconnects inside of the FPGA in order to be able to create my project and actually put it on the device. Any questions about that? Yes, go ahead.
Are we forced to use any vendor-provided or closed-source tools, or can you do the full chain?
My answer to you is depends on what blocks you want to use within that part. If you want to use some of those proprietary blocks, you have to use a proprietary tool. If you want to use the normal blocks that have been reverse engineered, the answer is you're not required to do it. You can use the open source tools. Allison.
I would think the logical natural desire would be to start with the circuit schematic that you want and hope to generate the net list out at the end.
You can actually do it either way. Most of the tools allow you to either use a schematic capture and turn that into an HDL if you come from the EE side of things. If you come from the programming side of things, you'll use a hardware description language like Verilog or VHDL, and then let it go ahead and do that for you.
You write a C program and it compiles to HDL? Is that what
No. Well, there are C to HDL, but they're not good. There's also HDL to C as well, but again, they're not great.
So maybe you're going to show an example.
If you want something that's C-like, use Verilog. It uses a lot of the C conventions. If you like Ada, like some of us do, then use VHDL, because it looks very much like Ada. It does. It's almost all the same. Okay. In the synthesis step, we're going to call it YOSYS, because that's the name of the tool that we're using, is YOSYS. And it converts the HDL into a netlist that can then be used by the next piece. Okay, matter of fact, we're going to talk right about YOSYS here. It's an HDL synthesis suite. It goes from Verilog as its HDL language to the netlist. Okay? It has some logic optimization and minimization. I don't remember what he's calling ABC here. What it does is it knows about the part that you're going to actually use it in. And because the reverse engineering that's been done already by Clifford in this particular case, he understands that this is the way to do the best optimization for this particular part. It supports the mapping. You'll notice that it overlaps with the place and route. It's trying to give the place and route every chance it can to do the most efficient use of that part, because you only have so many logic cells and so many clock lines and so much pieces of memory. So he's got some different mappings for different ASIC cell libraries. He's using little tiny ASICs in his research. He's also done some Series 7 FPGA stuff, and of course, the most significant one is the ICE40. That's where he started, and that's where things are going. This is where you can get all of the tools. Zephyr.at, Yosis, and you start there, and it's all there. So I'll leave this up for a minute so you can take a picture. That's where you get the actual open source tools. All right, everybody got it? All right, I'll move on then. So place and route. Place and route says, okay, we've got this intermediate step that looks like a net list of how I want things hooked up. It's been as optimized as it can because it understands what device you're actually going to talk to, and so the synthesis tool tries to give you the most optimized output net list so that it uses that chip efficiently, and then from there, it goes ahead and knows which one it's going to go. It has to know exactly which part you're going to program. And so the place and route actually knows what to do with that. It clumps netlist elements into larger blocks so that it can make it more efficient, places them in the blocks on the FPGA, and then routes the interconnect between them. So when you hear place, it's placing the logical elements in the blocks, and then the routing is how it's interconnected across it. You try and lump things in together to make them use these local interconnects, which there's lots of, rather than try and use these global interconnects, which there are fewer of. So, much like RAM and ROM, think of this is the RAM bus, and this is a much slower and longer path to go to some other block somewhere else. You want to try and use as much as possible these green ones because they're faster and there's more of them.
Why are they faster?
They're right next to it. They're on the same level, they're on the same piece of the fabric. They're right next to it. If you were to take a micrograph of it and open the lid on it and take a micrograph of it, you'd look at it, and they look like, you've seen the pictures of RAM blocks, you know. Well, think of it that the address lines and the data lines are right there, and then beyond that there's clock lines, and beyond that, and it just keeps going out further and further, and they may not even be on the same level and have to have interconnects that go between layers.
So it's not logic speed, it's literally speed of light distance.
It's all of that. It's all of everything. It's capacitance, it's the speed of light things, it's how much the fabric has available to it, how much of that. Very often in this thing you'll see that it has so much local interconnect, and then it'll say, I have so many other that are global interconnect, and I have so many local clock lines, and I have so many global clock lines.
Have you ever developed at that level?
The tool does. That's what the tool is doing for you.
Do we ever have reason to do it ourselves?
You can write your HDL in such a way that you try and block it for it and make it better for it as a module, and so that when it does the synthesis, it attempts to lump things together, so you can tweak your code.
Like writing C code that's easier to compile it out.
Pretty much. That's the same kind of thing. Only here we're optimizing the use of those logical elements and the buses that are surrounding them.
So directly writing this would be like writing hello world with ones and zeros.
You probably couldn't, because you don't know enough information about how this is organized to be able to do that. That's what the tool is capable of doing. Yes?
I'll add to that. When you lay up the board, you're designing laid up the board, you have a lot of freedom, so you can move things around so that the routing works well.
Mm-hmm.
But if you're using someone else's FPGA, like you're using a Terry Signal or one of these things, they've already pre-routed all the pins on the damn device, so that
Yep.
the router has to try to work around that.
Right, exactly. Okay. I keep coming back and referring to this because this is the hard part, is to get the concept of how, when we're writing a hardware description language, that we're talking about this, we're going to use this LUT because it's this logical unit, and we're going to use this register, which is your I/O piece. Yeah. Yeah. Exactly. All right. Place and route. Okay. So they pack. Again, this is all in the tool. We're not actually going to do this. We're going to try and help the tool, but the tool's going to do this itself. There's different versions of it, and they keep rewriting the place and route tool because that's the tool where the optimization really takes place. And so they've gone through iterations of, oh, we'll start doing this and it'll work, and it works in most of these cases, but not in this case. So they rewrite the tool again and try and make it work better and more efficiently and get more out of the parts. And then eventually they route all the interconnects between them. Okay. So the current version that's out now, which is the best for lattice parts, is called Next PNR, and it depends on the technology in which they're using as to which tool is better, or which tool is more mature, I should say, for that particular part. So you'll have to do research depending on whether you're going to use an Arctic 7 or a Spartan 7 versus using a lattice or some other part. Okay. All right. This is the place and route tool. It's called Next PNR. That's like generation 3 tool. It's timing driven. Remember, we're dealing with hardware. So since we're dealing with hardware, we have to figure out what is our constraint. What is the thing that's driving the whole tool? In this case, the tool is being driven by timing. It's trying to keep things that are using the same clocks and using the same elements close together. You ever heard of clock skew? Anybody heard of clock skew? It happens when you have this time of speed of light problem across the chip because the chip has capacitance in it. And so these global clock lines have skew in them when you go between logical blocks. So you want to, if things want to be lined up perfectly, you try and keep them in the same block. That's what this tool tries to do. It tries to keep those things that are using the same clock in the same block, or at least as close as possible, so that you don't end up with clock skew, so that they aren't off slightly. Works with Yocto. Again, that's the synthesis tool. Supports the lattice parts. These are the ones that he's worked on the most. You'll notice that he says has visualization support. We're visualizing what the timing looks like, and we'll see we'll see a demo of that in a bit. And then this is his Next PNR tool. If you go to his Clipper.at site and you go down and you go to the Yocto site, this Yocto HQ site, what you'll find is that it has a whole list of all these tools in order in how do you actually build them. You build them from scratch. It doesn't take long. It took, I think on my laptop it took about 45 minutes for everything. On the desktop it took about 20. All right. They then assemble. They take the placed and routed net list and they turn that into a bit stream. That bit stream is what can be then actually programmed into the device. Okay? This is where the secret sauce lays for the proprietary bits. The technology is undocumented by whoever, and this is where you have to do the reverse engineering. If we put these things in, what do we get out? Oh, okay, we got to tweak it to get what we want. And we figure out how it's arranged inside and how you program it as you go through this iterative process. And that's what's being done by the people who are working on this project, but on all the different architectures, whether it be ICE 40 or Arctic 7 or whatever. Any questions on any of this? I know it's a lot. All right. So, in keeping with their theme, they call it IcePack, which is the assembler. It's part of this IceStorm project. It turns the textual output of the place and route system into the binary bit stream. And that's the one that you can actually program into the device. Now, to make this easier, almost every one of the projects just uses a simple makefile that follows all the steps and makes it to where that it does all the steps in order. And you just give it the input files that you're going to use, and you create your own makefile, but there's a lot of places where you can use it as a starting place, and it makes it easier just to tweak them. And they're almost always MIT licensed, so it makes it really easy to use them in any project. Okay? So they use them, all the tools that we talked about are complete. That is to say, you can start with an HDL and you can end up with a bit stream that you can run in an actual device. So these aren't, oh, I can only go so far and then I've got to go somewhere else. It's all self-contained. IceStorm is primarily related to the Ice40. SymbaFlow is an overarching project that is looking to create something just like GCC for all the different architectures. So you mix and match the tools that are appropriate in order to make it so that you can effectively work with whatever parts you have. I'm going to show you a slide which I took when I was down at LCA recently. They had, let me just move this over. Okay, let me just show you this slide. This is actually a stop motion of the talk that I went to. So they're using Project Trellis, they're calling it. I just happen to stop it here, but it shows all of the tools. So in this particular case, because of Project Trellis, they're looking at, all these are separate projects that people are doing on their own. X-Ray and Trellis are these three right here are looking into different architectures and reverse engineering them. This is the synthesis tool, YOSYS, used by all of them. The architecture definitions, these are the ones that have been reverse engineered by these projects. And as they get, oh yeah, I understand how to make it to where that if you say this and we synthesize it down to something that it understands, that the place and route understands, then we actually can create the final output with it. Arachne PNR was the original place and route. It's been replaced by the second generation, which is the one we were just talking about, which is Next PNR. It also has a test and verification. It uses Icarus. Anybody used Icarus? It's iVerilog. It's an interactive Verilog like IPython. It also allows you to do visualization of it. But this is the overall flow that they're trying to do. You create an HDL. You tell it what architecture you're using. It goes ahead and uses a place and route. And then from there, it turns it in through the assembler into the actual bit stream that's going to be used. So it's very, very similar to what we're trying to do with, I'm just going to do it this way, to what we're trying to do with GCC. Let's see, I'm going to go ahead and close this right here. Okay. All right. So that is what SymbaFlow looks like. It's a little more, it's not as specific as IceStorm. Now the ICE tools and all these tools don't have a GUI interface to them. They're all done via command line. Again, it hasn't been turned into an IDE yet. Okay, any questions on any of that? Okay. All right. So we're going to talk mostly about IceStorm because that's the device I brought, is an Ice40 chip. Verilog to bitstream. It goes all the way from the hardware description language all the way until you get a bitstream that you can actually program into the device. The tools are Yosis, NextPNR, and IcePack. Those three all work together. There's also a programming tool called IceProg, and then there's a timing analysis tool called IceTime, and all of these are at this location. If you're familiar with C, Verilog is the easiest to start with because it uses most of the C constructs. All right. How many are used to using simulation and visualization tools? Okay. The one thing is, because we're using these tools for timing, you might want to look at the timing as to how the tools are going to create it and say, oh, that timing is off. That's why it doesn't work. You're going to have to actually, yep, this happens, this happens, this happens. Oh, that one's late. That's why it doesn't work, because that one's late. So you'll have to tweak your code in order to make it so that that happens on a particular clock cycle. You can also apply triggers and constraints. Constraints are usually in timing. I want this to happen 14 nanoseconds after something else happens, after the clock cycle. If you've not done it before, it's Greek, but once you start playing with it, it becomes a lot easier to see. And they're trying to make it so that you can actually do this visualization before you go to hardware. So you can actually see what's going on and make sure everything's lined up the way that you want it lined up. Okay? It's only used during development. It's not actually used in real life. Because it runs like every other emulator, it does not run in real time. It runs slower than that. Okay? So, let's talk about the design choices. A lot of this depends on what you're going to use is going to be based upon where you came from. If you come from C or Fortran, you're very likely to want to use Verilog. And the reason why is because it looks a lot like C. Very good support in the FOSS tools. As a matter of fact, it's the best supported in the FOSS tools. If you're a VHDL person like I am, you spend most of your time re-implementing things in Verilog. VHDL, oh, and by the way, this is not strongly typed, just like C. VHDL, however, is very strongly typed. It's influenced by Ada and Pascal and has type system. And then there's a whole bunch of other HDLs. This chisel based on SCaLE, if you know SCaLE. It's an abstraction on top of everything else. So it's like the C++ of that. What was that? Oh no. Wireless again being hit. Okay. All right. So this is the normal workflow that you would have. You'd implement it in the HDL. You'd simulate it using a test bench. You'd put stimulus into it. I've got a 10 megahertz clock. You go ahead and use that as your stimulus. You go ahead and iterate through getting everything timed the way that you want it to be timed. And then eventually you synthesize it to hardware. In very small test code, you can go ahead and eliminate the test bench state and just see what it does. And then you keep adjusting the HDL till you get it what you want. Just very similar to getting timing to work in C, right? If you've got something that's got very tight constraints, or you've got an ISR that's too long, you have to rewrite it until you get it to fit in the time frame allotted. Very similar with HDL. Remember, we're working at the hardware level, we're not working at software, so we're going to look at what's going on with a particular bit, and it may be something that's inside of the part, or you may be looking at the actual I/O that's around the part. So it could be all the way at the register level where you're looking at to see whether or not you're putting in the correct data into this register so that you can take it out again and use it for something else. All right. This is an example of iVerilog. Now this particular one, you've got some different output LEDs and you've got an input of a hardware clock. You assign the LEDs based on the count. You increment the counter, always at the positive edge of the hardware clock, and count is defined as count plus 1, and there's the end of your module. A register is a logical element. A wire is a physical element in this particular case. They call it the top of the top, and they have these are the definitions of the port that they're using. That's the definition they're looking at there. In this, what they're trying to do is they're trying to get the output of this simulation. This is a test bench piece, and they're trying to send that out to an LXT file. The output of running this simulation ends up going to this LXT file, which can then be looked at through GTK Wave. So, you run that. You run it through the VVP tool, so you see actually what's going on. It converts it to this. It converts the output to something that GTK can use, and then it starts to look like this. This is very hard to see. If I could turn off the lights for a minute, if somebody could turn off the lights, I could show this a little bit. No, you're going to have to use the right hand, lower right hand one. That one right there. Okay, see it now? So you can see that it has, this is the LED 1. It's going to blink at a faster rate. LED 2 is half the rate, and so on and so forth. You can see, you can look at the different signals specifically as to which output you care about and which one you turn on and off over here so that you can visualize it. You can see, okay, well, let's see, this one doesn't quite get turned on at the same time this one does. And it's only running at approximately half of the clock rate. And the same thing here, it just keeps moving. And that's because they haven't lined it up very well in their code. They haven't said on the positive edge, everything happens. So, oh, that may not be what I want to do, and I want to line up everything. Then you have to start tweaking your HDL code to make that happen, till it actually lines up the way you want it to line up. Go ahead and turn it back on again. Thanks. Any questions on that? All right. He's going to use the ice storm parts. Because this is a piece of hardware, we have to tell it what the pin map is from the internal pieces to the actual physical outside I/O. So we use a PCF file to do that. And you'll see that, and those are actually standard for whatever part you have. In addition to that, the pin map file, this PCF, is also used for if, let's say, a particular pin can only go so fast. If you try and make it go faster than that, it's simply not going to. You put the restraint information as to how fast that pin can go in this file, and it makes it so that when the synthesizing tool is actually trying to synthesize it, that it won't try and make that pin go too fast, where it can't go. All right. So there's all kinds of programmable logic devices available. Let me show you one that we have here. This is the iStick. It's $30, $29. It's got about 1,000 logic elements on it, and of course you can see it's got an LED on it. I programmed this with the tools that we have. This particular one today has a 6502 microprocessor in it. It has 4K of ROM and 4K of RAM available to it, and it has a piece of C code running in it, 6502C, and some assembly language. And it was all put into this, and all used open source tools. And that's all available out there on the net, and again, we use the single makefile for it. So you can get a lot done with one of these little things. And there's a lot of open source processors out there if you want to do that. Some of them are common, some of them are not common. You could use it as just without an operating system, or without having to have a processor in them. You could just use them as logic elements, depending on what you're trying to do with them. A lot of them have little pins on them so that they'll go onto one of the common boards. Use them for prototyping. This one has a ribbon cable as well, so that you can go off onto something else. This one runs at about 12 megahertz. I mean, this one, it only runs at about 12 megahertz. But they're inexpensive devices out there that you can start playing with today. Any questions? Yes?
If we've mastered that and we want to go on to bigger, better things, that particular product line, what is it scale?
The HX8 is 8K logical elements. The new version is, I think the latest version is 50K elements that you can actually use in something that you can use.
What about clock rates?
I've seen 60 to 80 megs. Yes, sir, in the back.
What types of applications would have like
Hundreds of input lines?
or like what you said that oh well we have a large amount of input lines, that's when we go to an FPGA. So I'm wondering what types of applications.
The places that I've seen them used a lot is in crypto, where they're used they're used a lot in crypto. They're used in video, where you've got a lot of data that you're trying to move back and forth. I've seen them used in other DSP applications. You may not need all of the I/O that it's capable of doing, but you need the internal bandwidth in order to be able to push 256 bits across at the same time when you're doing some math in FPGA math.
There's another place that is really important. You're doing real-time, hard real-time control.
Hard real-time.
You cannot afford to use ARM processor. You cannot afford to use any kind of infrastructure such as you have in Unity or FreeRTOS or any of these things. You must use hardware because you must be able to validate your time every time, 100% of the time.
Yep.
So it turns out, like in a Agonic application, you might have 100 inputs coming in or 50 inputs coming in, and what level you treat those inputs in when you process them, when they happen in consistent fashion. You simply can't do that with them.
You cannot do that with an ARM. Doesn't happen. Yes, go ahead.
And there is some research of offloading some STI stuff onto
Most of the time I'm using them as coke processors of some kind or another. Yes, sir.
Do you know of any open source IP for things like PCI or that sort of thing?
Not there yet. Getting close.
How about
Well, you could certainly, a PCI bus is a known thing, okay? It's not an unknown thing. The spec is out there. It's been out there forever, right? PCIe, same thing. The question is a question of whether you can make the timing constraints or not. You have to, that's where you spend the bulk of your time, isn't in writing the code, it's in making sure that the hardware can meet the timing constraints and signal requirements of the bus that you're trying to emulate.
Are there open source repositories of IP?
Yes. There's several of them. There's crypto, there's communications, there's all kinds of stuff. Yes, sir. Go back there.
So, use
Yes.
the analogy. You can basically compile in a debugging mode using the debugging symbol, and then you have your, maybe a discussion mode where you're shipping on that out, smaller package. Do you have the equivalent of that?
Yes, that's what I was going to show you. That's what we talked about earlier. Remember I said within this pin map here, this PCF file, you can put constraints in it. And those constraints allow you to say, oh, this particular pin isn't going to move any faster than this. Okay? And so, or I need this to happen 14 nanoseconds after something else happens. We can put that in there as well in some of the, in the code. All that code is part of the simulator code. That's what Icarus and iVerilog is used for. for creating, for turning that into something that you can visualize what the HDL is going to do. Now that's going to show you roughly how it's going to work. And I'm going to use the term roughly because that hasn't had the constraints of the actual physical device applied to it. When we write a test bench that includes the actual physical constraints of that particular device as applied to it, then it's a very accurate representation of all of those, of what it is it's actually going to do.
Okay, and follow up on that. If we get to a point where we have our running FPGA, where we're happy with how it's run on the FPGA, and we're ready to put it on basically production, something like that.
You mean like on an ASIC?
Maybe that, or maybe you're actually programming multiple FPGAs. Would you compile it differently and have a different bit stream come out, possibly stripping out?
Well, the typical way is that you try and make it so that that whatever it is you're emulating you're using is the same. So you put an FPGA board out there with all of its little I/O pins, and you plug that into something else, which is going to be your device that all the I/O is set up on. And if you've set up the constraints files correctly, these PCF files and some of the other pieces, it will very accurately emulate the final product.
Okay.
Of course, as soon as you turn the crank on a ASIC, it's $1 million, it's $10 million, it's $5 million, whatever it is, depending on which foundry you go to. Yes, sir.
When I learn something, I like to eventually get to the point of feeling like I fully understand how it's implemented from the bottom up. So when I was playing with Arduino, I was playing with the board, and then I wanted to learn the assembly for the -28S, and then buy the components and build it myself, which is pretty easy because all you need is a voltage regulator and a clock, for the most part.
Pretty much.
Okay, well, USB interface, you need that. FD guy. So if I start with a board like that, and then I want to get this working on a breadboard, what do I really need at a minimum?
Well, okay, so this looks like a 100-pin part. It's solderable by people who understand how to solder reasonably well. You can drag solder this by hand.
Or I could mount that in something with.
Or if you can get a carrier, this device in a carrier, you'll notice that it also has some pin outputs over here as well as this ribbon cable here. So 10th-inch center stuff. So that you've got some I/O options. If you want every bit of the I/O, you're going to have to build your own carrier. Okay? But you can. A lot of these, especially the low-end stuff, comes in 44-pin packages or 32-pin packages that are hand solderable. That's one of the reasons why it's changed from being, it's a 484-pin ball grid array, which is impossible to solder by hand, right? We know that. You're going to have an oven, you're going to have 6 to 8 layer board, maybe 12-layer board. That's why everybody says, I can't do FPGAs. You can do an FPGA with the little ones. And they're fairly reasonable as far as what they have. Like I said, this one right here has 4K of RAM and 4K of ROM, which means that if you have an assembly language program running in this processor, that's a lot of code and that's a lot of RAM. And it's cheap. This is $29.
But getting back to my question, if I buy that IC, what are the minimum components that I need to be able
Well, you need a clock, you need a power regulator, and you need some form of being able to do I/O, and some way to actually program it.
Basically the same situation as with microcontrollers.
Absolutely. There's oftentimes the older processors had multiple. The older versions of FPGAs had like 4 or 5 voltages that you were required to make them work. The newer ones, just simple single one, and they have an onboard regulator to solve a lot of the problems. So you don't have to have a 1.2 volt for internal and a 5 volt for this and a 3.3 for something else. The bit stream? The bit stream gets loaded usually into an SPI flash or directly loaded into the device via SPI. That's the normal way. Well, in this particular case, let me see. This one uses an FTDI, which emulates SPI. So it goes USB to SPI.
Right. But then how does that concept of the flash configure the data logic on the
Right, let's go back. What it does is it tells the fabric, when it's time to configure the fabric, way at the beginning, tells the fabric how to configure all these blocks, how to configure all these interconnects, how to configure all of the, which block gets which clock signal. All those things come from that. That's all part of that bit stream. That's all part of the encoded bit stream. I say it's encoded because it has the super secret sauce that tells this how to configure itself.
So,
Mm-hmm.
go back to your diagram again.
Okay, sure.
So you said,
This is a generic, by the way. This isn't a real thing.
so the FPGA that is the low end was 1,000, how much you said?
1,000 of these logical blocks. And they have so much block RAM, and they have so much stuff. And block RAM is what? It's a flip-flop. That's a bit, right? A block, and depending on, and by the way, you can configure these to be 8K, 1 bit times 8K, or 8 bits times 1K, or whatever configuration you want. If you want a 256-bit wide thing, knock yourself out. You can do that. Now, the timing gets to be a little challenging when you're trying to make that many things wide, right? Because they're probably not in a single block here. They're going to take multiple blocks in order to do that 256-bit wide thing. So timing gets to be a little challenging at times if you need to do that.
How many, like what, 8 slots per block possibly?
Depends on the device. Every device is different. So rather than say it's this, every single family is different, every single part is different. I know, it's not a standard because this is all secret sauce for whatever the fabric vendor is. No, depends on what family you're using, depends on what they're doing. There is no standard. I know. Right. Yes, in the back, sir.
What's the name of that package?
The what again?
The stick, the package.
Ice stick.
Yeah. And can it do analog?
There's no analog on it. Most FPGAs are not mixed signal. Now, there are a few that are mixed signal. The ones that I've used that are mixed signal generally start at about $1,200 a piece. So I try not to use them because they're a little out of my price range. Now, the one thing that's cool about this is, as we talked about earlier when somebody asked me about the analog to digital stuff, and that is an FPGA can be used to clear that high-speed ADC on a camera very, very quickly. Matter of fact, FPGAs are used, if you take a look at all of the high-speed stuff, it's almost always paired with an FPGA or a CPLD, some kind of logic that's really quick at making a FIFO. Any other questions? Okay. Thank you very much for your attention. I ran a little bit long, but that's okay. Thank you. Hi. Yep. Yeah. Oh, good. Even better.
It's one of these, right?
Yeah, it's one of those. One of those. How are you doing? I am. I was just about to ask you about the cable. I was going to come look for you. Oh, yeah, no worries. Oh, thank you. Hi. Good to meet you. We got a few of those. Thank you. Appreciate that. It was a little bit stressful at first to go, yeah.
What if I take a quick look at the ice set? Before I take a look at like the size and... So are you going to be posting that online?
Yeah.
Yeah, that'll be posted online. Okay.
Yep.
So did you cover some of the stuff I was asking about? I came in late, so I
yeah, you covered some of it. That's why.
Some pins, like a couple of LEDs just to play around with. Right. So just something like this is it's got
The goal
I think it's 1,000.
Proprietary tools that will sort of tools for all cases as much as possible.
Right, that's the goal. I'm saying
At this point, I'm seeing for academic research, as usual, academic research, and then follow it up so you don't have to line that. But those of us who don't want to spend thousands of dollars on tools, or that we develop a need that we should always have to use proprietary tools. If we don't want to use a proprietary tool and this tool is available, then we use this tool. If it's not completely done, that's a limitation of the tool and will happen as a result, just as a normal course of matters. It will change, and it has changed. When I first started looking at this, it could only handle block RAMs and some logic I/O elements. Now it can do a whole lot more than when we first started. So it's a lot more useful than it used to be.
Oh, for instance, in the case that you sent of microprocessor and RAM and ROM, that's a fairly sophisticated circuit.
Right, and it's all contained in that one piece.
Yeah.
And then the I/O comes out of that.
Now, of the 1,000 logic blocks, does the tool tell you like what percentage of them you
The processor and all of what I described to you takes 78% of this device. That includes the block RAM, all the block RAM and all the ROM, and the processor itself and all the logic elements for the I/O blocks, which there's two I/O blocks, there's a GPIO block and a something, essentially the demo that we had for it. I hate to do demos because we know that they always fail. So, yes.
Mine's about a quarter working.
No, that's pretty normal. I'm not worried about that. But all of that, takes about 78% of this device.
So plenty of room left for the
and
SPI that you were
for
working
the $40 device, it only takes 22%, which means it's got a whole lot more RAM available and a whole lot more ROM available. And by the way, we can add SPI and high-speed camera and all those other things that we want to as well, because it's available.
There's enough space. You ever use it for an application where you're not interfacing with external hardware, but kind of the way you'd use a video card with OpenSCaLE to have a parallel custom process, quick spinner up?
People use Bitcoin mine with it.
Right.
That's a standalone application pretty much.
It is. I guess I'm asking more, is it something where if you had a weekend to have to whip something up to solve a problem like that, would you say, nah, I'm going to do this with OpenSCaLE? I'll do it on a video card. Or would you say, I could just do it with my
really depends if I understand the algorithms correctly or not and can convert them into something the FPGA can use, or whether I would be better off to code it up in OpenSCaLE.
Are you asking for a lot more difficulty? Is it going to be a lot harder to do it for the FPGA? For like a quickie kind of application?
You really need to know...
Assuming you know the C code well, let's say, but so you're going to have to convert it either to Verilog or...
No, don't try to convert C code.
Well, that's your reference implementation.
No, you want to compute it for control. This is the two-field FPGA. Right. In the computing field, it's used as a coprocessor for a very limited application that it runs all the time. It's going to run that application all the time. It's going to do it this one thing. It's going to do it well because it's been coded up to do it well. It's not a GPIO. It's not a general purpose computer. Now, we made it into a general purpose computer because we realized that getting a 6502 and the RAM and everything else in order to teach this particular thing, to teach what we wanted to teach with it, was darn nearly impossible to buy a board like that anymore. And we wanted to teach something that was extremely simple. So that's why we did that. Extremely simple. What I use FPGA for is personally, I've used them a lot to replace things that I can no longer get that I'm required to have. Whether that be an obsolete Intel bus controller for making something work that has to be working for one of my clients, or I remember fondly programming in 6502 assembly, and I don't have a 6502 anymore, so I can do this, and I can have fun with it, and it's cheap. So that's what I use it for. On the high end, it's used for all the CFP applications in military and space and everything else. Used for ciphers, used for all kinds of wonderful stuff.
And good for glue logic.
Well, yeah, and that, especially the cheaper ones, replacement glue logic. Because right now we don't get glue logic anymore. It doesn't exist. I mean, you can't hardly go out and buy some of the glue anymore.
Well, what's glue logic? I'm sorry.
It's just logic. Logic gates, ands and OR gates, and all those things you might use for those things. 14, 16, yeah, absolutely, all of those. Absolutely, all of those. Okay, how you doing?
I'm like, laser project I work on created a circuit board that's kind of sandwiched between an FPGA and an FX3. So, and the FPGA handles the timing so the two ends talk to each other. And it can do 50, 80 megabytes a second.
This?
Yes, sorry, it's in the way there.
So what
I was trying to keep it out of everybody's way.
I was guarding it.
Oh, really?
Yeah. And then the software later you can modulate it and
Oh, really? Okay.
I don't have a talk about that.
Yeah, I'll have to get do that.
Come see me because I want that talk.
Oh, cool. Yeah. Well, I'm thinking the software will be pretty much finished by then, so
Yeah.
it should be a good talk.
Yeah.
What's the
You asked for a card.
like the
I mostly work in the broadcast environment. That's my actual application, so I
Well,
can't
they
talk about
have
some of that.
cards.
We use it a lot
They
for
have
multiplexers in
actual
FPGA. We use the FPGA for multiplexers.
and
So we can multiplex multiple video and audio signals together. And then ship them out over a transport and break them out on the other end.
Yeah, like this
Or so that we can mix them together so that we can have them transition between one scene to another scene, or fade in and fade out as you're going between streams. So stuff like that.
Special glue logic that there's so much I/O.
Yep.
You can have
Again, it's doing the thing.
way more flexible than they were on my open source. And a great example of that is this project. You can have emulators.
Because the foundry to do that is not easy. They use this technology to create the RISC-V that was just talked about before. They use the FPGA as the foundation for it. And then from there, they went ahead and turned it into silicon, real silicon, as opposed to, but they verified the whole thing through these HCL synthesis tools. So they probably use commercial tools because the other pieces are not available. To do an entire processor, large processor like they're doing, 32, 64, 128-bit wide thing, requires a big chip. Remember, I said you can either go 1 bit by 8 or, and just keep rearranging it. And then, of course, the performance takes a hit as you go across more logical blocks. So it slows down. Now, that doesn't mean, because it does scale up, that's just a limitation of the chip. That doesn't have to do with the architecture being inefficient or the architecture being a problem. That's just that particular device, which doesn't have, 128 bits worth of things in one logical block. The bigger parts might have that whole 128 in one logical block, so it doesn't have to be spread across multiple blocks and then time aligned across those blocks, which limits the speed. But that's just a question of what the thing is capable of doing of the part itself. Doesn't mean the design is wrong. The design can be verified using the analysis tools without actually being put into a hardware part. It can still be verified that the logic of it lines up and it works correctly. Oh, that's always fun. Now you carted this down from up north?
Yeah.
The whole thing? Did you drive or fly?
I drove. I'm going to Baja after this.
Oh, you're headed to Baja. Okay.
I'm gonna go play.
Well, yeah, I don't blame you. Especially if you come down this far.
Yes.
Get out of the rain and go down
with
there, right?
Well, we're having snow right now.
Oh, my goodness, you're having snow. Oh, my goodness. Okay. All right. So when it's time for you to talk, I'll help you set up your stuff over here and get this set up.
Okay.
Okay. I'll just let you go ahead and work on that.
Oh, I'm pretty much set. Yeah.
Okay, good. We've actually had a good number of.
So you volunteered here too?
I used to run AV here.
Oh, okay.
I used to run all of AV. My passion, however, is embedded. So when it became clear that I was tired of doing that after 10 years of running AV, I started this embedded track and started to make it because I was more interested in embedded. And I still wanted to continue to study people, and then I'm also doing training as well. So I'm doing embedded training. So that's keeping me busy. I go out to the Linux Foundation and teach for the Linux Foundation. So I go to different places, and yeah, it is. It's a lot of fun. And of course, embedded is always fun stuff.
Yeah, and I don't spend enough time to get used into it.
Like
I have and then I have other
responsibility.
Yeah,
I enjoy photography now too. I've learned that. I'm Tom.
Hi, Tom.
Good to meet you.
Good to meet you too.
All right. Well, glad you came. When I saw your talk, I said this will be fun.
Well, it doesn't sound like it's at the level of yours.
Well,
I think
actually,
it's fun for
this talk was the one that somebody else was supposed to give, and he couldn't make it over here, so he asked me if I would do it, and I said, sure, I'll go ahead and do it. And I really enjoy FPGAs because I've used them over the years. And
yeah,
it's
I've seen really interesting.
Oh.
Is this one of the Sega that's now open? And I saw talk about using it for power metering, right?
Yep, all that stuff. I know, it's a lot of fun.
It is.
Yep, a lot of fun stuff. Yep. Oh, longer than that. 99, 98, something like that. I know. We've done all kinds of crazy things. Okay, so depends on what your output is. What is? Oh, you've got a Thunderbolt?
We decided that VGA is going to be the game.
Oh, you have VGA output? Oh, you do already. Oh, you've got that already.
I went into the room and
well, no, you got it to work. That's going to be good enough. There you go. All right. Good. Okay. Let me go ahead. Let's see. Do you have a T-shirt on underneath that or not?
I'll take a T-shirt.
Huh?
Yeah.
Well, the reason why I'm asking is I like to put this down. I like to put this behind their back so that you don't do this. Whee! It flies across the room. Having been there and done that. And then you put this in your back pocket. So if you want to, you can put this here and then put this in the back pocket, and I'll get you set up. Okay. When you're ready. You don't have to do it right now. When you're ready for it, we'll go ahead and do that. Okay.
Yeah, I'll definitely be in touch then.
Okay.
Yeah, I figure I've got a year to work on it, and then I'll probably work on it in the 2 weeks before the due date.
Of course.
That's fine.
Well, you have to get in your abstract.
Yeah, exactly.
I'm good. you will do this. Yeah. Well, I wouldn't put it around your ear. Just like go like that. Now it's better. Now it's behind you. Now free. Now you're free without throwing it across the room like I did. You have to go find out later tonight, but I thought we were supposed to have the room until tomorrow. Okay, find out. You guys have got to find that out. Yep. Find that out. All right. So when it's time for you to talk, let me show you the button that you care about. The button you care about is this one right here. When you push this button, it will push your slides up. So let's see. Go ahead. And now it should blink. And now you can move your slides over there if you want. Let me move this. This happens all the time with this. There we go. Go ahead. There you go. There you go. Oh no, I end up having to take them out and run around the front. There you go. That'll work.
Wondering,
Just run it as just present. No. Whatever you want to do. Yeah, I generally stand in front and I use my presenter, so I don't generally stand behind here. But that's me. Because of the way that I've learned how to teach, where the laptop ends up over here and I have to point at the things that are on the screen so many times. No, I understand. I agree. You got to see it. Okay. It is indeed. Unfortunately. Trying to get them to change this to finish up.
Sometimes happens. Sometimes the room gets crowded and you get too hot.
Of course. Anyway, wonderful. Now,
none of you see Windows.
what?
None of you see Windows.
Oh, I see. Okay. Do I use my presenter?
I've got one.
Okay. There you go. That looks good. I'm going to move it over.
I'm going to do it the first way because I forgot to have notes on it.
Oh, yeah. Understood. Yeah, I didn't decide to use the notes. He wrote notes up for me.
I kind of don't need, but
I decided not to because I read through it enough times where I kind of remembered the notes that he wrote. I was presenting for somebody else who couldn't make it. So it was like, okay, gotta practice this.
When did that hand over?
Oh, about a week and a half ago. So it's not bad. I have to present things all the time. But, okay, that looks good. That really looks good, actually. Okay. You got your notes here?
No. Somewhere a window pops up. Okay. play the same game that I do.
Oh, yeah, all the time, all the time. Well, you have to have it when you go in some buildings and stuff like that.
Yeah.
They just won't let you.
Yeah.
1, 2, 3. 1, 2, 3, 4. Okay. No, on the box here. Okay, now it's on.
Testing.
Go ahead and test, Ken.
Test. 1, 2, 3.
Okay. 1, 2, okay. Good afternoon. Welcome to this afternoon's 3 o'clock session. We're going to be talking about the Internet of Thingies. And Ken Eshelby, did I say that right?
Yes, perfect.
We'll be talking about that this afternoon. Take it away.
All right, thanks for sticking around. Hope you had a good conference so far. So this talk is called Internet of Thingies. I've given it a couple years ago here with an older iteration of the microcontroller. So let's get into it. So I'm going to be a bad speaker and stand out here. So with any project electronic like this, you need to ask yourself what your goals are for it, and what are the parameters, what are the limitations, that kind of thing. So these are some general types of considerations, I guess. Power with, so actually let me stop and ask you, who's familiar with using microcontrollers and small electronics and things like that? Okay, so about half the room. So voltage and draw through these devices is a very important consideration because you can't always mix and match. If you do, you have to do a little more design sometimes and make it all work, but so that's why it's at the top. And these aren't really in order. How your devices will communicate, if that's what they're going to do. Things like community is important. If it's a dead community or not supported or is archaic, then you're kind of on your own, unless the Internet Archives has something. Things like that. So in terms of how to find something that fits your project, this is just an example in the direction that I was going with this project. So I was comparing microcontrollers that are pretty easily available, pretty inexpensive, and more capable. There are a lot of options out there. So even this kind of choice is overwhelming. So I'm going after the ESP32 in this case. This is an older project, and I have it on here because it's been bouncing around in a pickup truck in lots of horrible environments, just partly to test the durability of these things. This is a ESP8266 controller right there that it's just got 2 temperature sensors and shows it to a little OLED display. But that was one of my requirements because I'm interested in making, this is your basic Toyota LCD digital clock that pretty much everything in the 80s and 90s and 2000 had. And I wanted to replace it with something better, so I'm working on kind of a really multi-function display. Now I have a newer truck and it's got even more space to put things in, so I'm kind of in over my head. So language considerations. I put 2 up that are pretty popular, but there are quite large differences between them, I think. So again, depending upon how comfortable you are with a certain language, maybe there's a use for it and you can implement it on the project that you're interested in. For me, I'm using Arduino C++ basically because library availability, flexibility within the libraries. You have many options for the same type of device, so it's a pretty flexible setup. Takes little memory and works fast, even though my application really doesn't need speed. So back to power requirements. I'm repeating because I think this is pretty important thing. In the case that I'm working with on this project, I can deal up to higher voltage with devices, and so converting that down to your typical hobbyist microcontroller is kind of a trick. So it was very much on my mind looking at this. There's some communication considerations. The IP addressing down at the bottom. What I'm doing is going to be used on a small university campus. So how you do, if you're doing automatic addressing or static and you need to manage those devices, there are lots of dependencies that way to keep track of where things are, give them proper names, do everything you do for a network or system management use. And finally, community, I touched on it, but I think it's an important piece of it. I'm not really a fan of needing an app to get into a community, so that's why I crossed it out. The easier to access the community, I think, the better. And some people like going through apps, so you know, this is my opinion. So again, it's all about choose what fits best for your project and you, and what you're comfortable with, and that will get you started. Don't begin with barriers, I guess, would be the idea. So the chip that I'm using this time is the ESP32. It's the next generation, basically, of the 8266 that Espressif makes. It's a very capable chip. Here's a hopefully not a Chinese replica that of an original chip, but it's one of those things that it's sometimes hard to know. This in particular has a few features. It's got a battery port and charging logic built in, because these chips tend to be very efficient, or can be very efficient with power. It's got a built-in USB connector for programming, so it's kind of everything on one board, and I think it was like about $6, so incredibly cheap. I want to say like 4 or 5 years ago, when the 8266s came out, they were up around $50, $60 for a board, and now they're super inexpensive. So more on the 32. I think this is impressive. The amount of options you have, the amount of connectivity to different buses and different ways of communicating is astounding on this chip. A very common one that I'll be using is the I2C, and I'm very interested in using the CAN bus to get data out of my vehicles to make use of on displays or other kinds of things. So this will interface to that. I have a lot of learning to do before I get to that point, but you know, the possibilities are there, and they're built in a very inexpensive package. This chip is also a little special because it has a lot of options for power control or power management. With the one that interests me is the steep sleep mode, where there's it'll be the next slide, but it's an ultra low power coprocessor that it in and of itself can remain awake with the main core shut down, and it can even interact with sensors connected to the board and make decisions to wake up the main processor if certain things happen, however you program it in. So it's possibilities again. This would get you, you know, many months on a small lithium-ion power pack. So remote locations or very difficult to get power to, this could be a base for a nice project. Here's more about the ULP. And just some ideas of amp draws in the different modes and the different resources on it. The radio chips use a lot of power, but that also depends on what type of mode that you select it to be in. So in the 8266s, the older generation, there were a lot of manufacturers building different designs of boards. It was kind of a new frontier in a way. Arduino kind of really started, but then this came along and had built-in Wi-Fi, and that was pretty exciting. But in those days, you had to do this kind of double conversion to get an understanding of which pin was which, because you had standard diagrams, and then you had to go find or test and discover the pins to map it correctly. So on this chip, all you have to do is go to get a standard diagram of the 32, and you're basically numbering the pins as the label on the standards diagram. And here's an example of that. This is going to be the chip that I'm specifically working with. But here you see, I guess, the ESP32 labels, and these are all different buses possible and kind of the pin intended use. And this is the header that is on this particular board. But for example, if I want to use IO4 for one of my uses, I just define it in code as 4, and off you go. It's light years easier than it was in the past. So the board that I'm working with is a project on Hackaday.io. They were here. I think they were a sponsor. So I came across this somehow, and a guy was working on Power over Ethernet board. The W stands for wired. It does have Wi-Fi on it, and it fully works. It has Bluetooth, just like it has all the standard features of the ESP32. But wired was particularly interesting because on a campus and in multiple closets and data center rooms, running power is a hassle. So one wire to do everything, communication and power, was very attractive. And in a network environment, you have a lot of switch ports generally available, and switches are generally PoE now. This is an older switch that's just a 100 megabit switch, and it's the base level, the first sort of iteration of Power over Ethernet, and it works perfectly fine. It's probably $20 or $30 used, and there are a million of them out there. This is the basics of the chip. It's basically a standard chip with PoE added, and so a lot of the circuitry on the chip is dealing with power manipulation and the Ethernet communication, and then heat dissipation too, because that is a thing when you go to change different voltages. You've got 20 pins to work with, and you've got some options on how to power it as well. You don't need to use Ethernet, but that's the idea for it, so I would think that would be the use case. But you can power it off of off the V+ pin. As well, it can deliver some limited power to your peripherals. So fairly flexible kind of a board. Here's more about Power over Ethernet. Bless you. So this is the standard, and the board conforms to the standards. There's some details about delivery and kind of design of the board. This is all from the kind of overview data sheet that the project has. Here's the use case. Typical network closet has some, maybe some HVAC controls, maybe security controls, other things. I don't think it's this room, but typically we would see, I live in Oregon and it's wet, and we have a creek running through campus, and sometimes that causes trouble with buildings, and I'm dealing with 100-year-old plus buildings sometimes, so things get a little messy. So one of the use cases is I want to provide a way to detect water existing on the floor, so that we can get a hold of a situation before somebody loses power, things short out, and more trouble and expense occurs. So these are kind of my ideas for how I want to accomplish this. This is one of the sensors I want to use. This is just a temperature, humidity, and air pressure sensor. I've used it a lot. It's a good chip. I did kind of an evaluation of a few different sensors, and I ended up liking this because it was very regular, and the data that it returned was consistent in how it changed. Some chips will temperature, humidity changes, and they'll sit and sit and sit and then jump. And this one was more of a smooth arc that when things change. So I like it. It's simple to connect because it uses I2C, and that's basically 4 wires, a data, clock, and then ground and power. So it's super easy and it's inexpensive. I guess one note I'll say is don't get a chip that says BMP 180 without the E. That just means it's temperature and pressure only, so you won't get humidity if that's what you're after. They're more common a couple, 3 years ago, and now these are kind of more common. But there are plenty of other types of chips out there too. This has a lot of libraries for it, or a variety of libraries, so you have a few more options with it. It's not typically the one you see with Instructables or other kinds of projects. I'm going to run through some parts of the code. This is all in Arduino C++. So this is just sensor setup. So I have to identify the libraries I need. This can be an adventure sometimes, but this is a typical kind of a setup. I define the pins for the data and the clock, and again, it's that easy numbering scheme. I initialize the wire library and initialize it this way. Different chips, different libraries for different chips. Many approaches. So you kind of have to roll with the punches and use the one that accommodates you the best, I guess I would say. And the only thing in here is it's basically now BME is kind of the reference for, you can call it whatever you want, but it's the reference for accessing this sensor. Let's see. So this is initializing the chip and basically doing a check to make sure that you've wired it correctly or that something's not wrong. Actually, today I was setting one up and I had 2 wires crossed, and of course this came up. So I was like, are you kidding? Is something wrong with the board? And sure enough, pins were swapped. So yay for error checking. The Ethernet side is a different game. It's a bit of a hunt to understand how things are connected. I think because this isn't as common, and the library I am using is based upon the chip maker Espressif's library, and so I would say it's like very raw in form to typify it. So you have a lot of definitions going on here to pass along to bring the chip up, or that piece of it up. And so I'm going to go back and forth a little bit, but we'll go find some of these things, and it'll give you an example of what you may have to do sometimes to make these things work. So to start with, we have this clock mode, and I've got it set to the GPIO 0 input, right? And so how do you know to do that? Because there's usually not good instructions on this. And so that one lives, I thought it was down. Where the heck did it go? Am I blind? Right here. Clock in IO 0. And IO 0, this is the actual ESP32 chip. IO 0 is right here, and it is IO 0, so easy, right? I mean, once you find it, it's easy. Likewise, I know that this chip is a LAN 8720 based Ethernet, so that's like documentation. So that's easy to set, as well as the ETH type. It's easy to set. And then the next one is I guess it is for the LAN 8270. the power pin. So this is, I think, documentation as well to use the internal APLL source. So that's just kind of digging through documentation and matching things up and trying it and then being surprised that it works. The final two are these two, this MDIO and the MDC. And so that was a little bit of a hunt as well. They are right here, and it shows 13 and 12. And so you come over here and you find them right here, MDIO, MDC. So I guess the numbers don't match up on that one, and that turns into 17 and 16, which is, I'll get this right. Hang on. 16 and 17 were the ones on the diagram, and those are the two defined. So that's a little bit of the effort that can be involved in doing something like that. So the next, I guess, would be layer 2, layer 3 networking, like the logical kind of level. And so that was also kind of a bit of a journey to understand the way that these are done. When I first, the previous iteration of these, when I tried to statically give a static IP address to the chip that was a Wi-Fi chip, it ended up being really difficult to find how to do that. And I'm not good at reading libraries so well, so I'm getting better. But this is ultimately the same setup that I used for the previous generation. So IP addressing is not bad. I've got serial stuff in here because this acts as a validation that things are set up how I want them. So the other part of it too was that these don't really, well, they do and they don't come with a MAC address. Let's pretend they don't. And so what do you use for a MAC address? Because on a network, you can't have two of the same MACs or communication won't work. It's similar with IP address. So there is a concept of, like private IP address, there's a concept of local use MAC addresses. And so that ended up being the result of this. The chances that you run into trouble are pretty low, but it can happen. So it's worth it to research it and make sure you're not stepping on a server or something, your DNS server. So this is just for how to read a couple of values from the sensor, temperature and humidity. It's pretty straightforward. Again, toward the start, I said I just called it BME for the sensor, and so now it's doing the functions built into the library to get the data, and then just print it out to the serial console. Pretty straightforward. There's many examples on that kind of thing. Yeah?
If we might go back to...
Which one?
Yeah, right there. If you wanted to take that temperature and maybe upload it to a remote server, is there a Arduino library that allows you to
Yep.
connect to a remote server?
Many. It's all about defining, that's what this is. It's about defining how you're going to do it. And so I've done it in the past as building mini web server on the chip and scraping it for data with an XML collector or a HTTP collector. My intention this time is to use MQTT to push to its stream telemetry kind of a approach, so that if I chose in a different project to use like a battery powered one where you'd have everything very, very asleep, and maybe every 15 minutes you wake it up and send a little piece of data and it shuts back down so that you can extend the life of it. I can make use of that logic, and in this case it's all wired, so these are all the devices, and they're sending to a broker. They have client libraries running on it and configured, and I have two different examples here. One is to store this MQTT data in InfluxDB and graph it with Grafana. The other way is to use a network management system, and if it has streaming telemetry in it, take advantage of that, use it as the broker, put it into whatever its time series data store is, and send it to Grafana. And likewise, I drew this other path because I'm also interested in not only metrics, but alert conditions. So there are other mechanisms that can be involved in that. So there are a lot of options. That's 2 options, and I would say there's dozens more ways you can go about. You could do something as simple as have your chip send a syslog data, and then have Splunk or Elastic or whatever go and make use of the data that way and store it as a time series. So, I mean, lots of approaches to doing this. But the chip itself lends it to it because you can define whatever protocol you want, and you can define the message being sent pretty explicitly. So I think the sky's the limit in some way. So love it. That's why I went this route too, because you're not constricted to what a vendor defines the capability of the device to. You're kind of out on your own because you're programming it, and therefore you're a little responsible for it, or your team is, but you can choose everything. So it's not all smooth sailing. There are some general things I've learned over the years by multiples, because things will come dead and you will kill things, and and things will just get flaky, or maybe your solder leaks over and causes weird behavior that you can't find. I mean, there's so many electrical things that can go on. But prepare for it. And these are at a price level where it's not super hard to have multiple wiring, multiple power supplies. Yeah?
What do you know about the durability of the ESP32 under harsh conditions, like, say, high temperatures?
Nothing yet. I can tell you the 8266 is a champion, and so I do a lot of like off-road exploration, and I'm in dusty, sea, salty, hot, cold, many different environments. Like 110, 115, Death Valley, or hot day here. Yeah. Yep. They all have specs, and they're built to, they're well within that kind of stuff. So, yeah. I'm surprised the one in my old pickup is not dead yet, and happy that it's not dead yet. But, so yeah, so far so good. I haven't also built a lot of protection to the chip either. It's not enclosed. It's not in any kind of vibration resistant kind of setup, nothing. And it's just zip tied to the dash, and off it goes, right? So that's part of the testing, though. I intentionally did that to see what it could take. I worked for the state of Oregon as a network engineer for many years, and we had a flood router once, we called it, where it was submerged and for a day or two, and took weeks or whatever, let it dry out, cleaned it, all this kind of stuff, fired it up, and off it went. So it's an ancient router now, but some things tend to be super well built. So that probably gave me the idea to test this thing this way. It was the past experience. So IDEs are interesting. They're easy when you have this clean example and you go implement the steps and you do your thing and it works, and yay. But things get interesting when there are significant shifts in technology or devices that come up, and people want to adapt their application to the new thing so that people will use it, and it's a good thing. So that's when things get messy. Linux has been a better experience with using an IDE because the file system to me is cleaner. Like for Windows, you'll have like sudo kinds of folders, things that the system references, and it causes some havoc sometimes on a development environment, because assumed paths and things like that get really weird. So that's just been my experience. I've found Linux to be a much nicer environment to develop in. And then I alluded to the bottom part where, so when the ESP32 came out, everybody wanted to make their libraries work with it, right? So Adafruit, bless them, did some work and made the old libraries compatible with the new chips without a lot of hassle. But in doing that, right, they loaded requirements like you have to use the newest version of Arduino IDE, and you know you have these other things, and even then you may have to do housekeeping and cleaning up of things and moving things around and making it work. So you know, I think the struggle is worth it because you get a better understanding of how your environment works, and you can maybe do more with it, and it helps for troubleshooting, debugging. So mixed bag. Libraries are funny things because they're made by people, and people do things for the reasons they do them, right? To address their issue and make something work in the way that they chose, right? They don't make it for you, they made it for them. So being aware of that helps understand some difficulties you might run into in dealing with these things. So that's all I'm really trying to point out here. And so in my case, it stopped me for the moment from using MQTT as a telemetry streaming technology, because the library that the board works with doesn't work with the pub/sub client library, which is the Arduino or Adafruit's MQTT default kind of library, right? People have written many more libraries, so it's going to be an adventure in learning and trying to find the right fit. I've done this in the past, so I know it can be done, or I may need to modify a library myself or write one, and that just means I get to learn more things to make things work the way that I want them to. Other things that crop up are things that are hard-coded in libraries, which you don't expect to happen. But again, people write code, so why not? I know that I've been lazy in certain instances and done things like this, so why wouldn't somebody else, kind of a thing. So you just have to be aware that why isn't this working? Why isn't this working? Finally, you get to a point where okay, I need to look at everything and see if anything jumps out. And sometimes things are very well documented and leaps out, and you can deal with it and move on. But it's just more things to be aware of. Things can get weird. So this goes back to dealing with the issue I found in the Ethernet libraries. And again, it just makes me more excited to work on this and gain deeper understanding. The other things I ran into were these two pins, so for using the I2C bus for the sensor to use the data and clock, you see I2C0 and I2C0. However, 2 and 12 are a little special, come to find out, in that they can prevent you from uploading your code to the chip if you've got something attached to it. So that's bug reports, tickets on GitHub, things like that. You investigate and you eventually find it. However, because pin assignment are so easy for the ESP32 that you just pick something else and check it, make sure it works, make sure it doesn't smoke your sensor, and you're good to go. So the workaround's easy, but coming up against that, again, it's like that's another variety of ways that you can hit a bump. So that's the talk. I have some devices I was going to do a demo, but I don't think the demo is that exciting. I was going to just like breathe on it, show temperature, raise, and all that kind of stuff, but because I couldn't get MQTT working, I couldn't build the dashboard, do all the rest of the stuff that just shows you on a screen. So looking at console logs are kind of boring. But it works. The whole thing works. We have a stereolithography printer at the school, which I never knew anything about. It's liquid resin based, and it prints things upside down and builds the software builds the structure so that as it's printing it doesn't break, and there's lots of stuff to it. Unfortunately, after it cures, this material that happened to be in use is very brittle, so the idea was to, and I will, but this is the very first draft, was to build a network rack capable enclosure, so you can just bolt it to the rack and run an Ethernet cable and you're done. So I'll get to that point, but as I started drilling in it, even if you do fine size increment to get up to the size of hole you want, it still starts cracking. The edge of the bit will catch it and it'll just fracture things. So, you know, revision. But that's the idea with the switch. But this is just showing kind of an example of a few devices in action. And they all work. Ethernet works. They're all pingable. Another goal is to be able to update them over the wire and modify the code that way. So there's a lot of things, details I can work out. Yeah?
Notice there are different implementations, different vendors with different brands of that implement ESP32.
Many.
I'm just checking on Amazon. I noticed you had one that I think it's Lolo.
Yeah, Lowland.
Right.
Yep.
So when you made the selection to go to that one, did you consider the other different brands or just pick one out of the hat?
Partly that. AliExpress is how I tend to buy chips and components. So it had a price advantage, and that was about just over $6. You probably get breaks for every 5 or 10 or 20 that you get. I had used previously 8266s. I used Wemos chips, and this is I don't know exactly how it works, but this is like the same company, and like I said at the start, who knows if the chip I got or the board I got is a knockoff, but it seems to work well. Like there haven't been surprises yet, so I've got it here actually. You can check it out. Oh, and I don't know if where has it gone? Does anybody recognize the background? It's your cover of your program guide. Because some of us work at the last minute. So yeah, if you want to take a look, just be careful for static electricity. So probably don't touch too much. But thanks for attending.
Thank you.
Nice to meet you.
Show up at my door this morning. I took the apprentice Linux engineer track. Like, oh, I want to start doing this. I just actually have back and
And I didn't even go into about like water sensing, motion sensors, light intensity, air quality. Like there's a zillion things you can do.
This is an old Cisco switch?
Oh,
wow.
Yeah.
Sweet.
And we're still running some of those in production.
No.
Oh, it's cool. At university. At the university. Private? Public. Private. Yeah. There's no budget.
I took a Cisco course at the local community college here, and we're doing a bunch of Cisco
switches and routers. It looks really familiar. It's like, oh snap.
Which
That's
one
a
is
great
this? This is humidity or moisture or
They're both, yeah, temperature, humidity, and pressure. And then you can put in a reference pressure and get a rough altitude
Oh, really?
as
Okay.
well. So if you're in a mobile situation,
Yeah.
you kinda.
Right. Because I know, right? Because I have issues with that because GPS has the geoid and it's not the real elevation. It's the,
Yep.
Oh, that's very cool.
What's
Okay.
north and what's true north?
Right. Exactly. Right.
It is shifting.
Wow.
Yeah.
So you find that chip to be reliable?
Yeah.
Because I have I have 4 nodes at home. Well, actually 5 nodes at home. It's just reporting temperature to a remote server that I created, and then I have a TV mounted on our living room that that with a dashboard that I built, right? That shows the.
Yep, I have the same thing.
Right.
That's so cool. Because one of the things I wanted to know was how hot does it get in the attic?
Yeah. Oh, okay, gotcha.
How stable does the basement?
Gotcha.
Right?
Gotcha.
And so part of the attic was Zephyr, like, when can I go up and work in the attic, right? When's it not freezing and when's it not 120 degrees?
Gotcha. Gotcha. So I kind of enhanced mine with like adding like family activities to the dashboard.
Yeah.
Right, like things that I do with my children, my family. So things that and they have like recurring activities like, hey guys, take out the trash on a weekly basis, stuff like that, and they get points for doing that.
That's
right?
cool.
So I wanted to.
Fun thing. I don't have a family.
Yeah.
I have a dog.
Okay, gotcha.
But yeah, that'd be super cool to do stuff like that.
Yeah. So I wanted to ask you a question. Do you know anything about a project? I mean, a project / research that came out a few years ago. Either from MIT or Berkeley, one of those universities.
It's got 5 wires because I just didn't tear one off.
Okay. So there's really only 4 functional.
Yeah, some of those TME boards do have 5 and they use different bus.
Oh, really?
So yeah,
You have a choice?
Oh, so many choices.
Okay. That means these.
Yep.
And these are native fruit toys.
No.
No?
Nope. They're just that's Bosch. B is Bosch. BME 280.
Oh, wow. Okay.
So SI Silicon Instruments. They make one that's really good as well.
Okay. But I mean, where did you purchase this?
China.
Oh, okay.
AliExpress.
Oh, you did? Oh, Ali. Okay.
AliExpress.
AliExpress. Oh, that's a native fruit. That's like
The game, right? Or pay 5 to 10 more on Amazon, or pay 50 more on Amazon.
I'm gonna pay like $8, $8 to $9.
Yeah, but it's only experimental. Like money is like okay, $8.
Exactly. If I was gonna get serious, I'd go a different. Or if I was gonna build a board myself, right? You go through a lot more steps. Watching the guy build that board,
Oh, really?
You learn. And I've got a friend who's an electrical engineer that designs PCBs and stuff too.
Oh, wow.
So
That's awesome.
I'm aware of things. I don't know anything.
Have him do it, right?
Right. Well, I ask him a million questions.
Right.
Do you know what software you use? Like
To
Eagle?
design? Eagle?
Eagle? Yeah, that's what we use for my.
I want to say.
Yeah.
Well, I talked to.
Where are you studying?
I did.
Pasadena Community College.
Okay. Oh, wow. And you're doing fabrication?
Yeah, we actually fabricated. I fabricated a game that I made. It was pretty much a Simon Says game. Yeah, put a bunch of LEDs and switches, and then we used Eagle to do the schematic.
Is it a vocational program?
You're on your way to badge design.
Yeah, right. I don't know, man. This one's great.
Oh yeah, I saw someone. I forgot. It was the.
Even number DEF CON. Hardware back.
Hey, stuff like AliExpress, like L, like
A-L-I.
A-L-I.
Oh, okay, gotcha. Express.
They will be your friends forever.
Yes, you go there and you'll buy everything.
Every time you go in, they'll give you a coupon.
Yeah, right. And you will be thankful and you will use it. Guarantee, right?
Is that it?
Yep.
Cool.
Yeah, that U is their symbol.
Gotcha. What is their the delivery turnaround? Do you know? The shipping.
2 to 3 weeks. It depends.
Okay.
But generally, sometimes it's super fast because they'll stock warehouses in the States.
Yeah.
One here.
And it's like hit and miss, but sometimes.
Gotcha.
Yeah.
Cool.
Embedded class.
Thank you.
Talking about having reports done.
Awesome.
Oh,
Thanks.
nice.
And he was saying that basically you can basically set your watch by the time you click enter,
it'll be 6 weeks it'll show up as your goal.
Yeah.
I mean, and that's like fabbing the board, doing the assembly, everything.
Yeah, actually, my professor, when we sent in our schematics, he got our boards like within like a week or two.
He was doing like a run of 100.
Yeah, oh yeah, that's
with
right.
assembly, like surface mount assembly and all that. So, but he's like, it's like OSH, you can do OSH parts like turnarounds basically whenever they fill up the big, it's like an optimization program. So whenever they fill up the big board, they
cut them up and send it out.
Right. Cut them up, send it out to you. So I've heard the turnaround time of those is like days. You know?
No, and I was wondering the same thing too, because I was like, how is he gonna get all of our boards like done and shipped? And it's a 16-week class, so like designing it, putting it together, making sure that all the connections work is like weeks, you know. So like by the time finals come,
Well, it's funny because I took electronics when I went to college, and we did like we made a circuit board. It was an oscillator, a 2-transistor oscillator.
Yeah.
And I still have it. We designed the printed circuit board. We did all the calculations and everything. Right. And I have it. And you have to hook it up to the oscilloscope to see if it still works.
Oh, wow.
Yeah, but I was thinking, if you're in a class, you don't have much time. But the turnaround time on those is just really fast.
Yeah.
It's all custom.
Get your phone out again.
Yeah.
We put up we made an oscillator with two potentiometers, and we're able to switch like the pitch and like all that stuff. Yeah, and it was actually really cool to see it on the oscilloscope and how even like
that is a good point. I should put a little bit of
size of the lines and stuff, and like you can see just like different types of like like digital ones, it's like ones and zeros, you know, so you just see it's just like a straight line across and some of the, it was a pretty awesome class,
Move back up.
It's amazing what you can do these days.
It's unbelievable.
You might want to look into it. They have I think Tom, got here. He does the
Subscribe to that thing, man, and you
have one last year for
you'll go nuts. Oh man,
bus and stuff like that.
He's got stuff, NeoPixel.
This year I took
He's got stuff on that. It just goes on and on.
It's more like MicroPython.
Oh, nice.
It was really cool. Really cool.
I didn't know where the power was for it.
No, don't worry about it.
Yeah.
So I'm going to ask you to do me a favor. Take off the outer jack.
Object in a house.
Just the outer
by analyzing the Wi-Fi.
You're going to take it off anyway? It's cold, so I left mine on.
Yeah, I don't know.
Remember something like that. All I want to do is the one I want to put it through your back pocket for me. There's a project about Wi-Fi signal. No, just I think I remember seeing mapping stuff.
Yeah. They could literally, if someone was like a room somewhere, they could literally map that person.
That sounds like the best concept. But explain exactly how you pronounce your name so I don't screw it up.
That stuff gets to that point where it's like super.
There's so many variations of it. I know, but I'd rather get it right.
If I can't, I'm trying to get it right.
Yeah.
It turns into a lot of time.
Exactly.
Yep. I need a few minutes to set up.
No problem at all. Thank you.
Yeah, appreciate it.
Well, I appreciate you sticking around. The hall, and everybody's like rushing out and ready to go. Well, how far did I go over?
Oh, you didn't. I think you were pretty much right on.
So this is the roughly we're talking about.
That's the guy.
Okay. Gotcha.
And this is one in the cave.
Just right. So this one makes it, it's because of the internet port.
That's the trick.
Yeah.
And you can use power to power it.
Gotcha.
Another trick.
Oh, nice.
Are your FPGA there are two other boards out there, I think.
I know, that's what everybody tells me.
I think this is the better made one, but he did a crowdfund round, and I jumped I got an email like an hour later on there, give me some more. I want to try it and see. And so I'm assuming eventually these ended up being like about $45. This circuitry is not cheap.
Yeah, gotcha.
And dealing with the time involved in design and dealing with heat and all that stuff.
Well, it's not legacy, but it's open source. So, talk to us really about
Yeah, I have a few projects that at some point I created I used Arduino to open and close the window blind on my bedroom.
Yeah.
With a potentiometer.
Yep.
But now I'm looking to take that one step further. Just do like a voice command, or maybe program it so that a certain time in the morning gets automatically open up.
Yeah.
Right?
So are you doing, like servos yourself to control?
I bought a servo for that. I just hooked it up, and then you know how the servers have like some of those servers have a cross.
Yeah.
So I just build I just screw the pole of the blind. The stick that comes to the blind, I just screw it to that, right? And then just when it goes through the whole system.
I've seen people do some projects that are looking at into things as well to
Is designed to try and
right,
the rod
and tool
very similar to
part of the G.
But now what I want to open up the actual blind. My wife had like the curtains. I want to be able to just open up the curtains.
But a lot of it right now.
Open up the blind. But I don't know. I'm still trying to figure out how to.
And then before you
open up the curtains.
like the physical part.
Yes, exactly. They slide.
Yeah.
Right. So I'm trying to figure out what the hell to do.
I think you need two rods with a like a nut like thing on it, and then you turn and then that sticks to something.
Right.
And then that's there's enough strength in it to
Right.
hold it.
Gotcha. I could probably give that.
This is all like from 4x4 truck.
Gotcha.
The mechanical stuff.
Okay.
Right?
When you're ready,
I don't know how well it'd work, and I don't know.
you push this button,
Okay.
and it puts you on. Okay?
Okay, so let me see what it does.
Yeah, go ahead.
You should be able
That's
to
okay.
find.
It was there a second ago.
Yeah.
It got unplugged accidentally.
Oh, this thing is loose.
How you search.
Yeah, we're gonna have to. How's that? Is that better?
There you go. Hey, that's pretty good.
Oh, it manages dual screen automatically.
It did it.
Oh, nice.
And what? And is this a?
This is LibreOffice.
Okay. Well, that's even better.
I didn't even know it manages it because I see different.
Yeah, that's good.
Like think of like city.
1, 2, 3, 4. Okay.
Oh, let me see if something else will work.
We still got about 9 minutes.
Yeah, I want to see if something else will work.
Speak about. That's even more fun.
And then you can start searching. I use Google image search a lot because they seem to visually you can pick things out really fast. Maybe But yeah, cool. That'd be so awesome.
Yeah.
I want to do that too.
Right.
Now I've made a with an Arduino board. I've made a porch light. So it's detecting daylight and turning lights on or off based on that. So that light energy is not wasted.
Yep.
Because a lot longer days, like we don't need as much.
I want to do something similar. Someone is in the bedroom, right? Just turn the lights on, right?
Yep.
And I mean, with some exceptions, of course. Someone is there and it's like bedtime. Actually, turn them off, right?
Yep.
And then it's no one is there. Just turn them off.
Yep.
Yeah. And the other thing that I did is I created a schedule where I say I automatically turn the TV on and off. So just to show that dashboard that I was telling you about, right? And that is control. I control that to the web, and I get a signal back to my dash on my server. Setting it up. We decided to see whether it's on or off.
Yeah. Perfect. So I got kind of into trouble with that when I printed out the page. Now I'm like, I have to get a printer now.
Yeah.
It's not that kind of printer, but roll of filament kind of.
Right.
I don't know anything about printers, but doing the real basic design of the case and looking at looking like around at like the dash of the truck and fitting things, like you can just make it perfect.
Yeah.
The Ender is like $170 now. So. Is it? I'm looking at the first the first printer out of the UK.
The advantage of the Ender is that it's open hardware, open source.
Okay.
How reliable is it?
Pretty good.
Is it one of those where you start out with the thing and then you have to print parts to make the full
No.
thing?
It's out of the box. Everything assembly runs. They give you a little. You have to put it together. It's
Yeah.
Yeah, but it's totally used for the other thing.
What's the name?
Ender 3. Ender 3. Yeah, they came out with Ender 5 too.
Do you know the formula?
Sorry?
Do you know how bad the print?
Oh, or the size? You know, it's 200 millimeters cubed. Yeah. Okay. Yeah, it's a good size. But it's like one of the biggest online groups. There's a bunch of Facebook groups for it. That particular printer, and it's pretty hackable.
Yeah, so,
like it's less than $200. So.
Yeah.
There's a lot to think about for those things.
Yeah.
You know, multi-filament things and.
Yeah, there's Ender 3 and Ender 3 Pro. The biggest thing.
Oh, you know what?
The biggest thing about the Ender is that for that price you get a huge bed, you get a bunch of stuff. Like right before Christmas they were like, you know, some really low prices on it.
What's happening
My
here?
wife's a STEM teacher, and yeah, they're like I said, less than $200.
So does she do designs and bring things in?
She's still trying to figure out what she's gonna do.
So I just started using I have like 3 days to print something for this, right? What do I do? Start knowing nothing, right? And so Autodesk has a dumb little tool, a web design tool, right?
Right.
And unfortunately, the first thing they ask for is your birthday. But
Hold on. LibreOffice went crazy.
Okay.
LibreOffice went crazy.
Our Formlab printer.
Oh, okay, right. Yeah.
It happens.
There's a bunch of different ones. In fact, there's some really
It won't open the slides now.
that are
Okay,
they're 3D,
let's see.
like it's like clay modeling. So you start off with the layer of
Okay, this is a problem.
you have to do modeling that way, and then you hit it and it renders onto a 3D printer.
Okay.
Yeah. But the Autodesk one.
Yeah, about the
It wouldn't. Okay, why is it not loading up the slides now? It was working just a minute ago.
Oh, I know. I was panicking on mine too.
Anything, Ken?
Okay. Well, thank you for coming. It seems like people liked it.
I think so.
That's good.
I'm happy.
Yeah, good.
Last time I did this talk with the old chip at 14, SCaLE 14.
Yeah, I remember.
Somebody came up mad to me because I said something that he never knew existed, right? And he'd been looking for a long time and
Okay.
really frustrated about it. I'm like, I'm glad I made you mad.
Yeah, exactly.
That's the best compliment.
Exactly. Yeah. It's like, wait a minute, you know about that and I didn't. Well, it's kind of like when I tell people that there actually is open source tools for doing FPGA work. They go, I didn't know that was existed. I thought you had to use all the proprietary.
Yeah.
Aren't you guys in trouble for doing that? No. We reverse engineered it. Who cares? That's their problem. It is. You get a lot of fun.
Yeah,
Welcome.
trying to recover this thing.
Yeah.
Okay.
My son is like 55 mm per second.
Okay.
Yeah, you can crank them up pretty fast. But you know, it's all about, you know, it's all
Thanks for the
filament, how hot you're running it, like
all of that.
Yeah, it's like
It's a big trouble.
Yeah.
Okay.
I mean, we can't run ours in your league that fast.
No.
Because we can't push enough material.
Right.
But we have
The quality goes down and
Right. And we have about, which means that the pullback on it's not as good as the direct, so.
yeah, the end is above. The end is above.
Yeah, okay, so it's about,
But
okay.
it's you know,
So I've learned about it, but he knows, and of course, depending on what material, and usually what color of material also mattered. So if you had, just because you had PLA, you could do yellow at one speed and temperature, but you had to do pink at a different, and purple at a different speed and temperature.
different manufacturers.
All of that too. Is that better now?
This will have to do because theater mode did not work. It messes up everything else. Or let me see if I get rid of it. I know. Let me just use that PDF.
Yeah, you know, that's what I end up using is a PDF the whole time, right? I used to.
SCaLE.
Okay. Welcome, everybody. We're going to get started here in just a minute, as soon as he's ready.
Technical difficulty.
So this is the final talk of the embedded track for this year. We've been doing embedded since Thursday morning between training, IoT, and we're also doing OpenEmbedded down below, which is a build system, and then also this track today. And we've talked about FPGAs, and we've talked about new parts that are RISC-V and that's coming along. And Ken just talked about the Internet of Things and all the wonderful things we can do embedded. And now, Hunye?
Hanyu.
Hanyu. I got it right. Hanyu. I'm always getting it wrong.
Hard name.
Sorry, it's a hard name. Is going to talk to us about machine learning, which is a new field that a lot of people are spending a lot of time in. And right now, in the embedded space, it's really hot. So take it away.
Hello, everyone. Thank you for coming. Thank you for staying for the very last session of the conference here. I'm going to be talking about machine learning. The reason that I want to talk about this is that I've been working on several projects, mainly for a customer. I'm an independent consultant, so I work on all sorts of different things. Most of what I do is on a system level, getting embedded devices working there. And my customers typically are algorithm specialists. They understand all the stuff about machine learning, but they don't know about the actual underlying hardware. That's where we kind of work together there. But it's really interesting what they could do. They could take a sensor and all of a sudden get all sorts of information out of it there. So I figure, why not learn something about that? And since I went through all this stuff there, I noticed there were some difficult areas, like references they would point me to, academic papers, things like that there. Doesn't always make sense if you're coming from a system standpoint there. So what I did, went through there, figured out some of these things there, and I'm hoping that I could transfer some of this knowledge that I went through for you guys that want to do something simple. The goal here, just so that I have some kind of goal, is to be able to take a sensor, measure something there, and then tell me what it is. You might have seen something similar out there where people take a camera, they aim it at something, and they'll identify what it is. Similar idea, but on a much simpler level. So with that in mind, this is roughly the things I'll be going through there. It's not exactly the exact order, but some of the things, they kind of interact with each other. So the goals here, just so that we have boundaries and make things easy, is that whatever tools I'm using, it's going to be C-based. And it needs to be simple to build, because I don't want to waste time dealing with build issues, figuring out the build system, or you need this library, and then you go down this whole spiral where you want one library, another library, another library. You could, a lot of these tools out there, they are based on Python there. You could use Python. The problem with that is if you're trying to build an embedded device and you try to port it to something else there, you got to go build Python yourself, which means you got to support all the other things. And most of the time, Python, they tell you use pip install to pull these other things there. It's easy. If you're in a desktop, all the libraries are there. Well, pip install sometimes invokes a C compiler, so all of a sudden you have an embedded device that you need to have a working C compiler and a whole bunch of other tools. That's why I'm setting a goal of got to be simple, got to be C if possible. There's no virtual machines involved, no other weird libraries to pull in there. And as I just said, the goal would be, we'll be analyzing some kind of sample and be able to identify what it could do. Machine learning could certainly do a lot more there. Like I was hinting earlier, you could do things with cameras, identify pictures, but that's really getting ahead of ourselves. Let's look at something very simple where you just have a sensor and you're just processing a data there. So, and also just to keep this talk kind of finite, something that fits in the 1 hour format is that we won't be looking at images, though I will be talking about like things where you would do differently if it was a case of an image there. Another thing is that the inputs we'll be talking about would be static. They're fixed, they come from my sensor. So that means if I get a reading now, it's going to be independent of time. In contrast to a more dynamic input would be like a voice, a sound, where you have a time series. You have things where the time is actually an element in your input there. Another thing is we're looking at purely software options there. For some of the more complicated things there are certainly hardware accelerators. You could use GPUs. Some of the embedded processors have hardware that accelerates machine learning. But we're trying to figure out the basics here. So let's forget about all these acceleration options there. And another thing is I'm coming from an embedded background there. So I'm looking at this from an embedded device where you have control of the whole distribution there. You're not looking at desktop. You're not going to have something, let's say you're running Ubuntu, where you could just do apt-get whatever to install something there. So that feeds back into my first requirement. It needs to have relatively few dependencies, something that you could actually manage. Another side concern here is potentially licensing. Because you're building an embedded device, oftentimes there, if you go have some kind of really restrictive license, you really can't do too much with it just because what the license imposes there. So let's start with some of the basics there. What is machine learning? How is it going to be different from all the other things that you might have heard? Like traditionally, there's ways to look at data and then come up with some kind of identification of things there. Well, machine learning is basically just taking a bunch of inputs there, and you're making inferences based on something that you have trained the device for. So you're looking for patterns in the things that you have trained the machine with. That's, in a nutshell, what machine learning is. All the different forms there, be it images, sample identification, prediction of patterns there. They're taking inputs, whatever you use to make your prediction with, and you're trying to look for how well it matches a previously trained pattern there. That's your training data there. This is in some ways very similar to how a new kid, a young person would learn. You would, if you're first learning things there, you don't know what an apple is. You get shown a picture of a nice red apple, labeled apple there, and after a while, you've seen enough of that, you realize you go to the supermarket, that's an apple. Machine learning is very similar to this thing. Now let's look at how is this really different from something that you may have done before without machine learning there. Let's say you have a sensor that produces some kind of number output there, and you want to find out based on that sensor, what is that thing there? What do you just measure? Well, the traditional way may be something along the lines of, if the input is within a given range, you would say, it's this, basically, or what I'm calling outcome 1 here. If it's not that there, we look for, is the reading in a different range, and repeat that. Well, in the machine learning approach, what you would do is, you create a bunch of representative samples of those things there, and just label them. So you identify the machine. What are those readings there? Let's say you're reading, in case what my demo will be doing is, I'll be trying to identify fake sugar from regular sugar. So I made some measurements of what is the readings I get from sugar, what are readings that I get from fake sugar there, and I train the machine with that data there. Then I feed a new reading into there. The machine learning there will go through all that and determine, does this match a sugar pattern better, or does it match the non-sugar pattern better? You notice that one thing here is, you don't actually have to figure out thresholds. Machine learning will figure out how the thresholds different, how the different combinations are. So it takes that part of it, it simplifies it. Another thing to keep in mind is that machine learning, this is not a new idea. A lot of this stuff dates back to research from the late 70s, 80s there. The big difference right now is we have a lot of computing power, even in the embedded space, which typically tends to lag a little bit behind, compared to like a desktop machine. You still have a lot of computing power. This is the main thing that makes it practical. One of the big barriers that I found that whenever you look at a new topic or new subject is vocabulary. Everybody likes to use different vocabularies. They like to have their own abbreviations for things there, and it makes it very hard. Because if you don't know vocabulary, you try to reading documentation, tutorials, papers on there, you're just completely lost. While this is not a complete list I'm providing there, this is some of the more annoying terms that's run across there. Neural networks, I'll explain what they are later on there, but neural networks, they're described different ways depending on which different variation they are. There are artificial neural networks. That's to show that how they're different from the neurons in an actual biological subject like your brain. There is a DNN, a deep neural network. There's a convolutional neural network there where basically you apply convolution in front of the neural network. You have a recurrent neural network. That's a neural network where you take the output from a neural network and you feed it back into itself so you get a sense of time. So you could say, look at the previous set of readings there and make a decision based on what happened previously. Then there's a simple neural network. That's kind of the opposite of a deep neural network. Deep neural network is a network where you have one neural network that feeds into another one, which may feed into another one there. So you have a cascading chain of neural networks there. Another concept is, I'm not going to go through all these since I don't think I actually have time to go through all my slides and actually get to the end. I'm going to just point out some of the more important ones. Since the slides will be posted either on the SCaLE website or at least on my website, it will be available one way or another. Oh yes, labels. So when you train a machine there, you provide it with data there. And then you need to be able to tell the machine what that data associated with it. That name that you have there, that's called labeling your data there. And the training data is what they call the truth. This is what it is in the real world there. So a lot of times you might read about, yeah, if you get this much data there, you should divide your sample data into a half. We call that the truth, or you have some way of confirming that's the truth. You label that, use that for training, and then you could use the other half of the data there for test purposes. The other ones, they're useful to know, but I won't go into too much detail now, just in the interest of time. Okay, the overall flow, if you were to apply neural network, or not neural network specifically, but machine learning in general to a particular problem there, the first thing you need to do is just figure out how do you want to deal with the data? How do you want to deal with a problem? Build a model. Are you going to be taking measurements based on some specific characteristic there? You need to map it out. Ultimately, a computer works with numbers there. So you need to figure out what are you going to be measuring and how do you feed it in there. You can't just say, I'm going to be basing it on color and call it red, yellow, blue. Computers don't quite understand that. You need to look at, are you feeding it an RGB sequence? Are you feeding it input from my spectrometer? So you need to build up a model. Same thing with the output there. What are you actually going to be measuring there? Are you going to be measuring, are you going to be outputting names of things there, specific types, category, groups there? So you need to build a model. The next thing you need to do is have data. This could be something that you measure, or generally you will measure this kind of thing there, but sometimes you may have to have subjects that would do things. Like one example is, let's say you want to measure, or you want to try to figure out, is someone running around? So you may put an accelerometer on that person there, and then you take some measurements like accelerometer, and you feed into your machine learning system there. You train it with that data there, but that's the data. You need that data to tell the machine this is running, and you also probably need to tell the machine this is when it's not running. So you need to somehow create and identify data there. You can't just look at a book and say, oh, in theory it predicts that under these conditions you're running, or these conditions are true. That's usually not sufficient. You want to have real world data to train a machine there, and the data should cover a wide range. So it could be that you may have a short person running, if you want to use an example of running there. You may also want to have a really tall person running there. You may want to have examples of a person running to a very rough road there. Just different examples there. Just like if you have a kid there, you're trying to just teach him something there. You want to show him the different variations that are all mapped to the same thing there. That's why you need a proper training data that covers a range. Otherwise, the machine will not know all these other variations. Once you have all that data there, you need to give it to the machine learning algorithms there. It will go take all that thing there, and then it'll iterate through itself, build its own network, build up the internal models, coefficients, depending on which variation of machine learning you use there. And then after you have all that there, you need to somehow take the numbers and map it back to your problem there. It goes back to your model there. Remember, machines, they work with numbers, not actual text. Text is for human. So you need to do some mapping after you're done with all this stuff there. And I'll show you in more detail later on. Machine learning, there are all sorts of variations out there, but there's just two large categories that's generally in use there. There's a concept of a neural network. This is very similar to what would be the neurons in a brain, a biological. It's modeled after the same idea there. There are many different variants out there, as I mentioned in the previous, or the few slides back with the vocabulary. Depending on how you arrange the neurons there, you get different types of neural networks there, and that could be very confusing if you're just first time jumping in, looking at the stuff there. Another thing to know is that neural networks are just multiplication and addition. It's pretty straightforward. You just do a lot of multiplication and additions there. The other common type of machine learning is support vector machines there. This one basically says you have data there. The most common example, I'll have a diagram later on there, would be you have two sorts of inputs there, and you just somehow you figure out what's the best way to draw a line to separate two regions there, and then when you have new data, you figure out where it sits in that whole graph, and that's your output there. It's a very simple concept. It doesn't require a lot of CPU to do. The hardest thing in both of these cases is actually the training part where you have to teach the machine. Neural networks there. Now let's look into a little bit more detail about that there. A neural network is just an array of neurons. Neurons is a very similar idea, as I keep pointing out, similar to what's in a biological brain. And depending on how the different neurons are connected there, you have different types of neural network. Like if you have a deep neural network there, you would have an array of neurons there that would connect to another one there. Most of the common neural networks are fully connected, so sometimes if you want to build a specialized type of it, you may not want to have connectivity. By fully connected, and I'll have pictures, I think next slide or one more slide later on, where the neurons there, you may not want to have them all connected if you have too many of those there, so that's what would drive which particular type of neural network you have there. And a neuron, all it does is it just multiplies whatever input is by a particular weight. That's usually a number less than 1, and that's the neuron. When you connect to another neuron there, you add up all the outputs of all the different neurons there, and that's your output from there. So it's very simple. Yeah, the simplest neural network that you could build would be something that you would have an input layer, you have an inside layer that has all the different weights there, and then you have an output layer there that will give you your output or your predictions there. Okay, so neural networks there, trying to decide if I should, okay, yeah, it's worthwhile talking about this given, I'm just worried about time right now. The neural networks there, if you have the inputs of a neural network, you could apply other operations to it. It's not just simply machine learning by itself there. There's different things you could do. You could, let's say, convert your data instead of looking at images where you have a lot of pixels. These days there, if you have a phone camera, you talk about 13 million pixels, 20 million pixels there. Each pixel in turn has 3 values, red, green, RGB. That's a lot of data to feed in there. So one way of handling all that there is you apply convolution. Convolution, if you're not familiar with that, it's a filter. That's all it is. In the case of images, what a convolution would do is that it would try to identify features in there, be it a diagonal line, a vertical line, a particular curve there. So it tries to break up your image into primitives. So in a convolution neural network, what you might do, first thing you might do is apply a filter there to just reduce it down to features there, and there's a way of combining all the different convolutions to reduce that, say, 20 million pixel picture down to something much smaller, much more manageable. Once you have reduced it down enough times there, you could apply that as an input to a neural network, and the neural network will figure out, oh, this particular combination of features, that's what it must be. So that makes it a lot more manageable. The problem with doing this is training it. Training it, you need to figure out what filters you need to generate. And that takes a lot of computing power. That's why you may have seen all these references. Oh, we're training it. We need to have this so-and-so GPU there, or you need a server array. That's why that's the case. Okay, the neurons themselves there. Oh, one important thing is you have all these neurons connecting to each other. You may potentially chain them. The problem with chaining them and you're doing multiplication on them is they may potentially explode. Let's say you feed in something there and you wind up with a value that's greater than 1, you multiply it by something else there, and you do it too many times, you get much, much larger data. Well, there's a concept of a mapping function there. Usually is a non-linear function there. What it does is that it may potentially exaggerate some of the particular outputs there. You may not want this neural network to be just slowly, linearly changing things. You might want it to just suddenly snap to a particular thing there. Or you might want to limit the range. Let's say you want to limit the range from -1 to +1, so you know it's less than 1. That will guarantee that if you chain next one to it, the whole network wouldn't explode. And there's different functions that you could do that there. There's a common one called sigmoid, which is essentially a hyperbolic tangent that guarantees that your output would be between -1 and 1 there. Another one that's common is what I call ReLU. It's a rectifier, essentially a diode. All it says is if your input to this thing is anything below 0 or below, it's mapped to 0. Anything greater than 1, greater than 0, it'll be mapped to exactly the value there. And then anything greater than 1 itself will be mapped to 1. So it has a clamping effect, and it prevents your whole network from exploding. There, this is the picture that I keep alluding to. This is a simple neural network there. You have your 3 layers, your input, that's where your values that you provide to your machine is available. This image is from Wikipedia, so you could take a picture of it, but you could also go to Wikipedia. It's from there. You have your input layer. That's basically all that does is this takes input there and it feeds in there. And then you have a hidden layer, which has all the different weights that does the multiplication, and your output is your output prediction there. All those different lines that connect to each one of those circles there, that's your connectivity there. All those lines means that it's their addition. So let's say in this layer, with these neurons there, this one multiplies each one of these guys there by a particular value. That's the weight. It takes that, and then that's the output of this one there. So it goes to this one, and depending on how that sum of the output, this one, it will give a value to this. Same thing here, this value will be composed of the output of this one, and this one. And if it's done right there, this may be, say, a high number, this might be a low number, whichever is your maximum would be your predicted output. Now let's look at the other common kind of machine learning. That's a support vector machine. Like I said earlier, basically all you're doing is that you're taking a data, you're dividing your data space into different regions there, and that's pretty much the whole process there. This whole thing runs very well on relatively low power CPUs. I've seen this running on something like a Cortex M0 if you're familiar with that. That's pretty much the simplest of all the current modern ARM microcontroller CPUs out there. And here's a picture of it. This is another picture I borrowed from Wikipedia. It's probably not the most ideal picture, but it illustrates the concept there. You have your data space, which is composed of 2 inputs, x1 and x2 there. And you have 2 different types of outputs there. One's represented by the circle that's open. The other one's represented by a fully filled out circle there. And these lines represent potential ways of breaking up space into 2 different kinds of outputs there. You have H1 there, which doesn't really separate out doesn't fully separate black and the white dots here. You have H2, which does separate the black and white dots here, but it's not ideal. You have noticed that it's much closer to the black compared to the white ones there, whereas H3 tries to keep an equal distance between those 2. That way, if you have some data that may, say, land right here, this will be classified as white there. But if you have data right here, if you use this one there, it will be potentially incorrectly classified as one of those members of this black dot. So conceptually, this is very simple. Now, those are the basics of that. Let's look at some of the software packages out there. The first link that I have up there is a list of a lot of different packages that's available there. So if you really don't care for all the C stuff that I'm talking about there, you want to go with some of the Python options there, they probably have some offerings there. So it's worthwhile looking through, see if there's something that's more comfortable for what you have. The first group is what we would call the commercial offerings there. They are usually backed by a company, and sometimes they're actually used internally by the company there. Or you may be able to actually buy a service to use those things there. I personally have some concerns about using those in that category just because it's backed by the company. If the company decides to somehow stop using it, is that going to be completely abandoned? What's going to happen to it there? Is it really tuned specifically for what they're using? Does it really fit what I'm using? So it's really up to what you think there. The first one there, the TensorFlow from Google, that's particularly notable is that Google has been making a lot of effort to try to get people to use that one there. You could pick up kits that would demonstrate TensorFlow at like Target. They have a little, I think it's a Raspberry Pi kit there with a camera, and you could do some basic image recognition on there. There's, I think, even an onboard accelerator for machine learning on there, and it all runs this stuff with TensorFlow. It's common. You might have heard a lot about that there, but that one pretty much forces you onto the Python track there and also kind of ties you to that particular package. The second group there is what is the open source offerings. Some of them may not necessarily be commercial friendly. So if you're looking at doing something for a company, you need to look at the license. One particular note is the SVM Lite there. The author has particularly mentioned that he really prefers it to be used for research. And while I didn't actually read the license text there, if that's what his preferences are, I think it's best to just respect that. The license might be freer, but if that's what the author wants, let's respect that. From that list there's two things there that's relatively simple. There is darknet, which is specific to images there, but that was incredibly simple and easy to build there. So if you want to look at images there, that might be a simple package. It doesn't require too many libraries there. It can even make use of GPU for acceleration on there, but just in the interest of time, and as I said, I'm not going to go into images here in this talk. I'm going to just leave it at that. The other package there is fan. That's the one that I'll be using for examples and demos here. It's a relatively simple package there. It's all written in C, and some examples there in the code could fit all in one slide. That's how simple it is. And usually people say, yeah, I could do the same thing with Python. Well, Python calls all these other objects, which calls other objects there, and you have to do the underlying build system. It just becomes a lot more convoluted there. Hardware acceleration, while it's not particularly applicable to what I'm going to be doing with the simple stuff there for learning, it's good to keep in mind that these things do exist if you want to go on further, look at the more difficult things, especially if you want to do something with vision there. The first is the Movidius compute stick from Intel there. This is a accelerator. It's relatively closed. If you are doing something that matches what they have provided as examples there, it may work. I think that's pretty much all that is. GPUs, that's a common thing for accelerating, especially on the training side. A GPU, if you're not that familiar with it, is basically a supercomputer. It does a lot of parallel operations very, very quickly there, and that's why it's useful for this machine learning stuff there. For using a GPU, there's three basic approaches there. If you're using NVIDIA hardware, either on embedded stuff or even on a desktop there, you can use the CUDA. NVIDIA does have an ARM chip with GPU on there that I believe supports CUDA. Or if you're doing something else there, or that's not NVIDIA's GPU there, there's OpenCL. I believe that's also available even on some of the ARM devices. Or worst case, you could always fall back to OpenGL, OpenGL ES. While that's specifically designed for graphical things there, you could still use it for computation. You just need to look at things a little bit differently. In the case of OpenCL, CUDA there, things are pretty simple. You give it data, and it does this thing. Well, in the case of using OpenGL or GLES, you need to tell it, oh, I have a texture. A texture is a 2D array, but your texture could really be your data itself there. And they have something they call shaders. Shaders are programmable. It's short snippets of code that looks a lot like C. It runs on, I think, every single one of those pixels there that you've provided there, and output there is another texture. So if you map your problem to something like that there, you could potentially use the GPU for acceleration. And of course, there's FPGA. You could always use hardware for acceleration for this kind of thing. Or even some of the newer chips there, like for example, I think if you have seen some of the BeagleBone stuff there, there's a newly announced board called a BeagleBoard AI. It uses the onboard video accelerator repurposed to do machine learning. TI has a software kit called TIDL, and you could do a lot of the vision stuff using just that. Okay, let's look at data. As I mentioned earlier, I'll be focusing mainly on static data. What that means is the data there doesn't really have a time element. You're not looking at a time series, so you're not looking at, for example, audio. Having said that there, that doesn't necessarily preclude you from doing some kind of processing involving that. You may have to phrase your problem slightly differently. But to keep things simple, let's just break it up into different categories, because you're also looking at potentially different algorithms for handling things there. Like for example, if you're looking at microphone, accelerometer output there, you're probably going to be using other algorithm like LSTM, long-term, short-term memory, where you may feed the output of the neural network back into itself as an input so that you have some sense of history there. And depending on how you do the feedback, you may have a long history or a short history there. And there's even other variants there which may involve the history there. And then images. This is really a special case of spatial data there. For if you want to treat things as the image, that means you could do certain things. Like for example, as I was alluding earlier, you could do convolution on there. You could do filtering. That doesn't necessarily apply if you just have a 2D array of data there, because convolution may not necessarily apply there. When you do convolution, you're making assumptions that there's a pixel that's spatially to next to you, above you, and below you, and so forth. Whereas if you just have 2D data there, that doesn't necessarily imply the case there. So that's one important thing to keep in mind. And by filtering there, I'm really referring to convolution if you're not familiar with, with what convolution does. Okay, the data itself there, as I was saying earlier, all the data that a computer deals with, they're numbers. That's all they are. To apply any meaning there, it's really up to you as the programmer, designer, basically human is what applies there. But within the numbers there, there's a few things that you need to keep in mind there. We're dealing usually with small numbers here, which range from 0 to 1, so you're multiplying things unless you want things to explode there. You're dealing with small constants there. Well, small constants there, depending on how it's represented by a computer, could have several issues. One is 0 multiplied by anything is going to be 0. So if you somehow get your number, you multiply by a small thing, and you're stuck near 0, it may get rounded down or truncated to 0, in which case that may not necessarily be very useful there. So now this drives the issue of precision. You may have potentially double precision. That could potentially help you get smaller numbers there. But the problem with doing things like double precision or even simple version, simple floating point, is you need floating point hardware to do a lot of multiplication. That implies performance issues there. So one way that for embedded devices people have worked around that is to use the concept of a fixed point. All that is instead of using, let's say, a number, 8-bit number, normally 8-bit will go from 0 to 255. You scale it. So instead of going from 0 to 55, you say you divide that by a fixed number. Let's say you divide it by a factor of 2. So now all of a sudden you get, say, 0 to 128. Each number has a granularity of 0.5. By adjusting that, you could get different level of granularity. By doing this, by just doing this simple scaling, you could just use normal integer multiplication there and just remember to scale later. So that removes the requirement to have a lot of processing power. It does not require you to have a floating point unit. Another thing to keep in mind is the computer. Is this a number? You may be doing a physical experiment. You might be measuring, say, accelerometer. Accelerometers could measure in G's, which may go from 0 to some hopefully small number. Or it may measure in meters per second square, which may be somewhere like 0 to some much larger number. The ranges there may not be convenient for computers. If you're looking at simple binary numbers, scaling it, you may go from, let's say, 0 to 128, but you're measuring G's, you're only using a small portion of it. So even without dealing with fixed point issues there, it may be useful to just do some scaling. So a unit doesn't really matter when you're feeding things into a computer there. And then the way you map all these features and numbers there, that could also impact your training time. Because if you have really large numbers there, you wind up hitting the activation function, and then things get clamped there, it will have a much harder time finding out appropriate weights for that there. So the range that you provide there could make a big difference in your overall model. You could have things that work, but it could take forever to train, which is not necessarily very useful. And similarly, for the mapping of numbers there, you have the input, obviously, you have some number sensors there. A lot of times the particular thing is not going to be a number. You're going to have to map that number or translate that number into something that's appropriate for a problem. If you're doing a simple identification, it may be translating that into a name. Another thing that's important to know is that with machine learning, generally your inputs there, you're dealing with an array of numbers. You're not dealing with a single number. So let's say you have 18 inputs, like what I'll be using for my spectrometer there. That's an array there. So a lot of times there, you're dealing with vectors, and you're doing vector multiplication there. If you have any kind of hardware or any kind of element that may speed it up, that would potentially help it a lot there. And just as a side note there, the name TensorFlow, the package from Google, well, tensors are basically arrays of numbers there. That's kind of where they came from. Preprocessing. This is preprocessing. This is a method where you may somehow massage your data a little bit that may help things there. Like I said earlier there, I'm going to focus mainly on static data there. But you kind of still have static data at the same time have some kind of time-dependent input. Let's say, for example, you could potentially process a microphone input by looking at derivatives of the signal there, integrals of the signal. There's different processing that you could do. You may potentially simplify your training if you just eliminate all the noise. You want to do some focus on particular things there, you could apply a filter ahead of the input data there. Or you're looking at where things are. You're doing some kind of measurement identification there. For training purposes, it actually matters depending on your data if it's a polar input where you have like say degree and then distance from a center point there, your origin, versus a certain more common X and Y rectilinear thing there. It comes down to what does your data, which one produces a more obvious pattern there. So that's something that it's not always obvious that you will just know offhand. Everything that I've read so far suggests that it comes down to experimentation. Sometimes some things will come off faster, sometimes it doesn't there. Similarly, with the space conversion, I would call it space conversion, but that's a poor choice of words just because I'll be confusing with that. What's called domain conversion is that you could be looking at your data in time space, or you could be looking at in, say, frequency space, or there's all sorts of other transforms there. The most common one would be like a Fourier transform. You could also potentially apply like a Poisson transform. Depending on the type of data, you could look at different spaces there, and that could help with training there, and it could also help with the potential identification process later on. Another thing is, if you have a lot of data there, let's say you have some really high sample rate coming in there, you could play games like average out the inputs there, combine multiple samples together there. What that's really doing there a lot of times is you're basically, when you average samples, you're applying a low-pass filter. Low-pass filter can sometimes help reduce the amount of noise in your data there. You could also do things like just simply, instead of combining discrete samples, let's say you have 10 samples coming in, instead of averaging every 2, you could have a rolling average there. So whereas every 3, you do an average, and then you drop the first one and you add another one there, so you have a rolling average. There's different games that you can play there, and that could potentially help you improve your data itself there. If there's something in your pattern that involves figuring out a maximum, minimum there, it may be useful to feed more than just your actual sample data in there. You may want to feed the first derivative of the data, second derivative of the data there. It really comes down to your problem, because machine learning is not magic. If it helps you as a person to actually figure out what's going on there, that particular processing data may be helpful to find for machine learning. Because machine learning, all it's doing is looking for patterns. If you have some way of processing data so that the pattern is more obvious, and that could reduce your computational load, both on the training side and potentially on the prediction side. The first point is very important. Machine learning, it's not magic. If you feed it garbage, your training data is no good there, or you just don't give it enough data there, you're just going to get garbage out. It's not going to be able to predict things from nothing. One way of looking at this is, if you have a problem, you have an expert, let's say that's in another country, if you give it the same data that you would give the machine over a phone line, and that expert cannot give you a reasonable answer or a meaningful answer based on what you asked that, you probably don't have enough data. That's probably the simplest way to look at this. Another thing that may not be obvious that I ran across in many references, your training data. There's apparently a magic sweet point there. If you have too much training data, the risk there you have is the patterns that machine learning will find will match things so precisely, it will only predict things in your training data set there. On the other hand, if you don't give it enough training data there, the machine doesn't know what it's going to be looking at there. So there's kind of a balancing point that you need to do there. The other problem with having too much data is it can take too long to train. Now comes the interesting part of machine learning, or the training part. I would consider the interesting part there. It all comes down to a very brute force process. Most of these algorithms, and there are several different algorithms for trying to train a machine there. When you train a machine, especially with neural networks there, all you're doing is you're trying to find the weights for each one of those neurons there. Depending on how many neurons you have, it could be a lot of different weights that you need to determine there. The process is essentially, you start out with some random numbers. You put some random coefficients into your neural networks there. You run your training data through that thing there. It could be just one sample depending on your particular algorithm you're using, or you can send all your data through there, and you compare it with what it expects. That's your labels, as I mentioned earlier. You compare those things there. You compute an error based on that, and by using the error, you could feed it back and adjust those weights there, and you iterate. You keep iterating until your error goes below a certain particular threshold, and then once you have that, you're done. So this is purely a brute force thing, and it could take a long, long time. With SVM, it's very similar to this thing there, but it's a little bit closer to math. But I'm not going to say that much more about SVM just because it gets used, but it's also not the more common one that gets used. Because of this brute force approach there, it sometimes helps to have like a giant server farm. So some of the more complicated machine learning algorithms, you could potentially parallelize it either over multiple CPUs. You could parallelize it over the different individual bits of the GPU there. So I mentioned earlier, a GPU, what it does is it takes pretty much all the pixels that it has there and it runs it all in parallel. So it's a giant parallel computer, and it does a lot of multiplications there. In graphics programming, you may have to adjust shading based on particular coefficients. That's pretty much what we're doing in machine learning. So it's very similar, and it runs in parallel, and it's available at mostly a reasonable cost. The other half of machine learning is the prediction/inference phase there, depending on what you're trying to do. If you're trying to, say, look at a pattern in the stock market and then predict what's going to happen next day, that would be referred to as a prediction there. If you're trying to look at samples there and match it up to what you had before, what you trained the machine with, that would be called inference. But it's basically the same thing. It's the output of your machine learning there. This part, unlike the machine learning, the training side of it, doesn't require as much CPU. It can often be run on some simple microcontrollers there. Like I said, you could potentially run it on something as small as a Cortex M0, and M4 is not unreasonable if it's not overly complicated there. After all you're doing is doing multiplication and additions there. And I think I covered that. I kind of went out of order, so I covered most of that. And the output of your prediction thing. Generally, when you have an output of prediction thing, it will give you an array of numbers there. These are sometimes you might have seen some examples out there, especially with the cameras. They say, oh, this is 60% prediction that this may be a person, 25% that this may be a car there, even though it may obviously not be a car there. These numbers are the outputs of different neurons there. And generally, if you want to identify what something is there, is when you get the output there, where you have each value is probability is what is referred to, but it's not exactly a probability. But I'll just use that term anyway, since it seems to get confused with that anyways. Each value will be a probability that is a match for that particular thing there. And what you want to do is you want to go through the whole array, find the highest value, the most probable item, and then just call it, that's my prediction there. So that's generally your output. Now, tying this thing back to embedded things. Look at the time. Oh, okay. Okay. Hopefully, I might have to drop off some of the bits there, but feel free to interrupt with questions if I'm going a bit too fast, or raise your hands or say something there. For embedded devices, that's mainly my focus there. You need to think about, are you going to be using floating point numbers on there? A lot of embedded devices, especially if you're not running Linux on there, even though this is a Linux conference, may not be able to handle floating point numbers that quickly. You may be emulating in software. That might not be ideal. Even with Linux there, if you don't have a hardware FPU there, it could be painfully slow. Or you have it, maybe your FPU only does single point precision. Like I think on the ARM Neon, it only does single point there. If you want to have double precision, you need to make sure you're using a core that actually has the, I think the VFP unit there. So that's, you need to make sure your data really fits what you have in your processor. Otherwise, really weird things in the performance side can happen there. Software licenses. A lot of times when you're building an embedded device there, you're probably not expecting it to be kind of ripped up and redone there. Even though you may be building an open source thing, it might be a useful thing for you're still combining potentially several different pieces of software. It's very important to know what are the licenses, and if you have a library that references another library, which references another library, they may be compatible if you're using that on a desktop, but if you're using it somewhere else there, that might impose additional restrictions on your device. This is part of the reason why I was really trying to avoid looking at Python, just because Python pip install whatever, looks easy, but unless you know exactly what's pulling in there, that could get you into a lot of trouble later on. Okay, yeah, I'm running short on time here. Okay, now let's look at the thing that I was trying to build. Like I was, just to recap earlier there, I'm trying to build a device here, just mainly for learning. It's not really a product at all. I'm trying to device that uses a spectrometer and looks at a sample, and it tells me, is it real sugar? Is it a fake sugar, like aspartame, equal, any of those other things there? And for hardware, I'm going to use a BeagleBone just because it's a nice Linux computer there. Most of what I do on desktop is just kind of a drop in there. And it interfaces easily with my development board for the spectrometer that I'm using there. And I'm going to use desktop CPU for just training there. I've tried using training on the BeagleBone itself there, the same code. It works. I stopped it after about 2 hours. It just took too long there. Whereas on a laptop, actually this particular laptop I'm using for presentation, I think it's an Intel i5 there. It takes maybe about a minute or two to do the same training there. And the software package I'll be using to do this is Fan. It's reasonably mature, it's been around for a while, and it's simple to build. Essentially, you go in there, it's CMake, and then just make yourself. It doesn't really have any major library dependencies other than, I think, algebraic library, which is commonly included. And then they also have versions of it which would use a fixed point map, so it would be helpful if you have to do that on an embedded device. And Fan is written in C. If you want to still use Fan, there are bindings available for other languages. Like, for example, online I found a tutorial for using Fan with PHP, if you like that. I think there's also bindings for Python, if you also like that there. So you don't really have to use C. It just C is easy to understand what the pieces are. You don't have these hidden pieces coming in. Okay, just to show you how simple this is. For fan training, this is the example that you find the website there. Essentially what they're trying to do is, in this whole example, they're trying to emulate the XOR function. You have two inputs there, it's your basic gate, and you have one output there. And this is the code. Use fan for training that. The first half up to about here is all declarations there. The first one there just kind of gives nice names to how you want to define your network there. You have a basic two inputs that represents your two inputs for the XOR. You have one output, that's your output for your XOR, and then total number of layers. You have your input layer, the hidden inside layer, and then the output layer. That's your 3. And then we have 3 neurons there. That's somewhat of an arbitrary number that seems to work well. And for training, we need to find out how accurate do we want to be. This is the one value I was telling you earlier where you just kind of iterate over and over again until you find that the error is acceptable. In this case, we set the threshold to 0.001. And what's the worst case before it gives up there? It will try this up to 500,000 times, and every 1,000 times it'll just give me some statistical output on where it is. Where is the error, how big it is roughly. It gives me an idea that am I getting somewhere? If it doesn't look like I'm getting somewhere, maybe I'm doing something wrong. So it's a useful thing. The trade-off there is that you have too much output. It may wind up wasting a lot of time just doing output there, so you probably don't want to set this to like 1. And to create the neural network there, you pretty much just call this thing there with those values. And all they're doing is just using nice names for it. So if you want to get rid of those lines, just put in numbers there. And we want to configure the neural network to use activation number. In this case, we're using sigmoid we're using sigmoid for both the hidden layer and also the output layer. And then we're training it on a text file there. You could also give it individual samples, but in this case, just to make things simple there, we're giving it a file to read. It'll run through this thing there. When it's done, it'll save that to output so that we can use it later, and the rest is just cleanup there. So incredibly simple, and this is all written in C. Now let's look at the training data there. First line just tells the fan how many samples I have and what the samples look like there. The first value is a number of different samples there. We're doing XOR, so there's only 4 possible combinations. Each one of the samples has 2 inputs, and each one of the samples has 1 output. That's the 1. And then -1 in this case means it's false. 1 is true. So if you have 2 falses, you also get a false, and so forth there. So this is your training data there. For what I'm doing, I'll show you that later. It's very similar. It's a very simple text file. And then after you train the thing, you want to be able to use it. This is pretty simple. All you're doing is you're creating the neural network there based on the weights that you found earlier from the training there. It loads that in there, and then we're going to run it through. We're going to set up two inputs there. In this case, -1 and 1. We run it through the network there, and then we print the output, and all we're doing is repeating that. In this case, we're just looking at the raw outputs there, in which case it would be a number. In the case of a slightly more interesting application, like what I'll be doing, I'll probably be taking that number and then having an array that maps that to a name, but this is pretty simple there. Okay, this is pretty much a block diagram of my little demo hardware that I put together there. There's 18-channel spectrometer there. That's the one that measures the light. It also has a little light to reflect it off of there. It all feeds into the BeagleBone. And just to make things simple, since the BeagleBone doesn't have a display, I'm going to send it over a network, and I'm going to use a standard protocol. Use MQTT there, so I could just use like a Mosquito and just dump that on the screen. Makes it easy to debug. And if I want to, it's easy to slap a nice UI on there. Okay, let's look at training. Let's actually go to a console. In this case, I'm doing the training on a laptop. That's x86 one. I've tried it. Okay. Yep, run it, train. Before I do that, I'll just show you what this is pretty much the example I have earlier. The biggest difference is going to be in this line there. I find that it's a little bit faster if I configure to use a slightly different strategy for finding the coefficients there in the neural network there. Other than that, this is pretty much the examples there. I bumped up the number of epochs there just in case I need to go through more. I reduced the error a little bit. And yeah, this is pretty much the example. And train. So all it's doing now is that it started with a random number there, and from there it's trying to find an optimal strategy for getting to something that matches the output there. The bit failure, that's a number of outputs that just are completely wrong from what it was expected to be. The current error, that's the total error for all the outputs there, and it's just iterating over each time it tries different combinations based on the previous pass there. And one other change that from the previous example, I think it outputs every 1,000 epochs. Right now I'm outputting about every 2,000 epochs. It doesn't take that much longer. It should converge pretty soon. But even for something simple like this,
how big are your data sets?
There, this is done. I'll show you the data set. This is the data. There's 18 samples in here. Each one of the sample has 18 readings there. They represent the 18 channels of my spectrometer there. And I have a 25 member vector output that basically tells me what kind of artificial sugar. Is it Splenda? Is it equal? And so forth there. And then the last, I think, 4-bit, it represents is it sugar or not. There's also some that I haven't actually defined, so it just mapped to false. But this is my training set. There's 18 entries in here. So it's not overly large, and yet it takes a noticeable amount of time. And it takes much longer if you were to run it on the target itself. Okay, and let's see if I get back to the slide. LibreOffice wasn't behaving nicely. Yeah. Okay, that's the training. And then running, the process what we'll be doing is that I'll be collecting data there. I'll do some pre-processing, which basically means I'm just scaling the data from the range that the spectrometer provides into, I think, a range between 0 and 1, then feeding to a neural network, and then I'm mapping the output to a name there. That code, I'll show you that code later. Let's try running this first. Okay. So what I've done is that I've built up a little board which adds a switch. Basically, it's a GPIO thing that triggers off the whole process, so I don't have to actually log in there manually do that. And right now, I have the spectrometer sitting on a sample of Splenda. And that's the output. For this particular thing, since it's a demo there, I purposely made it more verbose. The outputs here, that's actually the output for the spectrometer. And this is the output for the neural network there. It found that the maximum for a specific identification is 0.76. It's roughly about 76% it believes is aspartame, which is, I think, what Splenda is, and then is a sugar substitute. For identifying all these different sugar substitutes, one thing I found is, if you do some research on these guys, is they're a very small amount of particular sugar substitute, and a lot of it is filler. Apparently, that stuff is very potent. It's like 1 or 2% of it is aspartame. The rest is some kind of a filler. I think dextrose seems to be a common one, and that's common with pretty much all the other ones. So sometimes this neural network gets confused. It would misidentify aspartame, but I find that it's reasonably accurate on the sugar side. So let's try this again with actual sugar. And do I have stuff stuck here? Let's try this again. Okay, it's misbehaving right now. Oh, wait. Got distributed sugar around so that the spectrometer doesn't see the tablecloth. Still not. It was working earlier, but just so that I don't keep you guys here in case you guys have flights there. My session's almost over. Okay, let's go back to the slides. So where did it go? Okay, that's mostly a demo there. Oh yeah, another thing to keep in mind, if you're doing machine learning, you might want to consider how are you using the data? Where are you getting a training set from there? I don't have an answer for this, and it may be something more for a lawyer to tell you. Is the data, let's say, you find on the internet, is that considered to be fair use of it, or do you really need a license for it? That's something to think about, because Google has access to a lot of things there, and are they using your data that you provided there? They may have found a search engine. Who knows? But that's something that you should keep in mind. Another thing is open source licensing there. Your training, your little network, in my case, that little .NET file there, is that really part of the same copyright as same license as your regular code there. Because a lot of times the licenses don't really apply to data. After all, I am loading this as data there, so should my potentially GPO code apply to that particular network there, or is it separate? That's something, again, to think about. It may be, again, a lawyer thing. And also with machine learning, things are a little bit imprecise. So how do you QA these things there? And again, it's another question to think about. Because normally, if you do, let's say, a more traditional way, you have thresholds there, you could potentially iterate through all the thresholds there and see, look at the output. But since each time each time you train it, you could potentially get different weights there. How do you know this is correct? Do you just sample a few of them and hope that it works? Something to think about. So, yeah, in the interest of time, I'm going to skip ahead. If you want to look more into that, I had plans to log into the Buildroot and show you the code there, but I don't want to keep you guys here too late. Any questions? Yes?
Basically, for this machine learning, it depends upon with the data set, the trained data set. Once it's trained, that's it.
Yep.
So can you make it like, dynamic learning? Like you do something, recognize, oh, this is wrong, and you learn it more dynamic.
You could potentially do that there, but the problem with doing it on an actual embedded device is training takes so much longer time there. Do you have the processing power to do that there? One way potentially you could do that is to do this in batches there. Let's say you have a connected device. You could save the data there, and then if it's wrong, or have someone tell you it's wrong there, save what's wrong, add it to your data set, and then train it and periodically provide updates to your network there, and that will improve your data. But all this really comes down to how good is your training data. If your training data is garbage, your output's going to be garbage. Yes?
How do you deal with hyperparameter training?
Sorry?
How do you deal with hyperparameter training?
Hyperparameter training?
The number of iterations to go through and the number of samples to go through and so on and so forth. So if you go back to your code,
right,
at the beginning of it, there are so many parameters that you set up.
Right.
Like, I think one of them was like 80,000. And
let's go to, where is that? Oh, where? Okay, yeah. Right, which parameter?
Right there. So the number of epochs and desired error and training rate. So those are called, collectively, those are called hyperparameters.
Oh, okay, that's what you're referring to, okay.
Yeah, so I noticed in there, obviously, you have them hard-coded, but if, for training purposes, I mean, you may have to provide different type of combinations to get the right number of, to reduce the error rate.
Right.
So how do you personally manage that?
I personally manage it largely by experimentation. One thing to keep in mind is, like, for example, max epoch, that is actually an upper bound on things there. If it keeps failing below that, then I start investigating, okay, is there something wrong with the model, or is it really that complicated to do that thing? Or maybe I don't have enough neurons there. That's when it's more a flag to me to go, okay, there's something I need to tune there. Or it may just simply be it's a difficult problem. So it's more of a trial and error. There really isn't a good thing. And I did some research on this thing that most people do say is largely trial and error.
Yeah, I had a kind of a related question to that. In a more typical machine learning shop, you're going to have your data set, and you're going to decide, like in the case of neural network, you are going to have hyperparameters, how many layers, how many neurons per layer, are they fully connected, things like that. And then you're going to do a lot of cross-validation on your training data, right? So you're going to leave out 10%, train with 90%.
Yes.
Repeating that over and over. I'm kind of concerned that maybe a model like this, especially one where you set that desired error level in advance, is just completely overfitting on your training set. And if we were to take your device and have someone run out and grab like their own sucrose or whatever out of the center here, it might actually fail on those ones because
Yes.
It just seems, I mean, coming from a more traditional machine learning background, it seems a little kind of different.
Yes. No, actually, the way that everything that I've come across, and that includes talking to people about this, the way you manage that is actually the way you partition your data there. That's why earlier I said you generally partition about like 50% of your data, hopefully randomly, as your training set, and the other 50%. Because if you do like a 90-10 split there, it may be very specific to your training data. And like what you pointed out earlier there, I might be very specific to what I have there. So there's definitely that problem there. That's something to definitely watch out for. Oh, it doesn't come with a camera. I'm actually not using a camera. I'm using a development board. What it has is that it has 18 channels of sensors in there. It's done by filters and photodiodes. It connects over a virtual serial port, which interfaces over the USB port. That's separate. This is a development board by AMS who makes that sensor. I think there's another question.
Yeah, so for your training data, do you have to feed that format into SCAN, or does SCAN do the representation of like the formatted your data, or does it expect, like can you just have like 18 vectors and just feed it to SCAN and then that will train?
Okay, there's two ways you could go about that. One way is that you could use a different function in FAN there where you just feed it a sample at a time there. That's one way of training it. That could potentially be very painful. The other way is that you have to use that specific format and you just write a script to do that there. Like for example, the output from my sensor, it actually is a whole bunch of slightly different format data there. And I have, actually if you want to, I can show you the script later. I have a simple awk script that reads that text file, converts to that format, and outputs that there. Because in my that data there, I actually annotate it so I have more information in there than what FAN needs, but that tells me what I need to do. It also has the human readable names, so I can always go back and check things. Any other questions? Right.
Do you happen to know of any FPGAs being used for machine learning training? Is that like?
Nothing specific.
This is like a new area that's becoming active now? Or?
Well, there is some of the stuff that I think Google is doing there is can be done on FPGAs there. A lot of the deep learning stuff there.
People trying to recreate the GPU basic chips onto the...
Yes, yes. Any other questions? Okay. Thank you for coming. Hope this was somewhat useful, you guys. Oh, yeah, this is a development board. Oh, yeah, it's a development board, that's all that is.
Okay. And how did you, oh, you just put it over the top of the...
Yeah, like this. I think I may have at the wrong angle, it was seen through the wrapper.
It's merciful, right?
Yeah, it's not the best spectrometer either. It's 18 channels, crude, but it was cheap.
Very cool.
Is there a website that has all the additions that you can add for? Like where did you get the spectrum?
Oh, this guy, this is a development board by AMS. They made sensors there. It normally interfaces your PC over this, but they use the AT command set. So as an Abigo board, it's pretty much a PC, plug it in. Yeah. The only thing I really made is this thing to give me a switch.
And you mounted it on a PVC?
Yeah, PVC, because I don't want to get ambient light. So if you look in there, that thing is flat. So if I hold it too close, it won't get a proper field of view there. This thing just, nice cheap thing. Yeah.
Like mount it.
Yeah, that's all it is. And it keeps out light.
How much was it for?
This board, I think, was like maybe about $90 from DigiKey. There's a project there to build like a $25 spectrometer. We use the exact same chipset, except that one you got to cut some traces to use it in the UART mode, which is what I'm using there. By default, it comes with I2C, which is a little bit more work to get it working here. Hmm?
How much is the spectrometer?
Oh, this guy is a development board for about $90 there. Yeah, there's a project that uses the same chips there. I think like SparkFun, they have a version for $50, but that's wired up for I2C instead of a UART. The chip supports both.
I see.
And you can cut some traces and convert it.
Do you mind if I take a picture?
Go ahead.
So it's dry sugar you're looking at. You're not looking at like sugar in a drink.
No.
Checking to see if you've got sugar or
There's no reason why you can't. You could potentially do that there. The only problem there is now you gotta have a rig that gives you like probably what is it? Cuvettes. That's what the labs use. It's almost like a glass container with a thing that passes out light there. You got to put the sample in there. It's just more complicated.
Seems like there's a lot of uses for it.
Yeah.
Like food safety or drug testing.
Yeah, that's what, if you look at YouTube, AMS actually has a video where they have a nice little app there written that will identify 3 different substances. They're all white.
Whoa.
So, but I'm just trying to replicate what they have there. They wouldn't, I don't think they provide the sources or any information about that particular demo.
And how would I find that on YouTube? Just search for
probably search for the company, AMS.
Oh, AMS.
Yeah, AMS, they make sensors there. Like AMS spectrometer, that might be good. And then see if it's from the manufacturer. I think it's a demo video from them.
Did I understand? This is like looking at the light
Yeah.
that comes from the thing, and there's some characteristic appearance of the 2 different kinds of powder, sugar and the non-sugar.
Yep.
And then is there some baseline that you have in your computer that characterize what sugar is supposed to look like?
No.
It doesn't need that.
It doesn't need that. What you do is that I take measurements from different samples there, and that just, and I label that sugar. Then I run it through a training, so it tries to look for it. Does it match that pattern?
So that kind of becomes a baseline.
Yeah, exactly.
Then a given further sample is referred back.
Yes. Yeah, so that's the difference, because traditionally you would have a baseline there, and you try, how close is it, maybe how far can you be off by that and still call it sugar there. That would probably be a more traditional way. With machine learning, you give it a whole bunch of data there, it'll try to match out figure out a pattern, and then when you do the prediction phase, it will say, which is the closest to that pattern? If so, that must be it.
You know, example you gave, and also I've been looking at this very recently, saw some other stuff online. They talk about just 2 dimensions, points. And grouping the points in the upper left and the lower right. These are black and these are white.
Right.
But like with chemical sugar, like there could be a whole multiple number of different characteristics that could be involved in
Mhm.
investigation?
Right.
How do you handle that?
The
Some
same.
kind of multidimensional math thing?
Yes, exactly. They just have a line that divides it. They have a concept called a hyperplane,
Okay.
and it gets a lot hairier when you get to multiple dimensions there.
And then what was that fan thing you were using? Is that something that knows how to do this kind of stuff?
Okay.
Library that knows how to do it?
There's two different concepts I think you're mixing up there. There is neural networks, and then there's something called support vector machine. That's the SVM. So SVM does what you just talked about with the line that divides up things there. With neural networks there, you don't really have the concept of that lines there. All you're doing is you're building up different weights for the neurons there, and then that gets summed up, and then looking at which is the largest number, that's the output. So it's two different approaches to that. Fan does neural networks.
Thank you very much.
Hey, if I wanted to measure the sample of the water in my household,
Right.
what instruments do you recommend that I could use, or what type of sensor would you recommend?
What are you looking for in the
I'm
water?
looking for particles in the water to, to detect if it's how clean it is.
Okay, so you're basically measuring turbidity. That's what.
Okay.
For that, it could be something as simple as something like a light, and you measure the light output data. Once if you got particles in there, it'll probably scatter and it'll impact the amount of light.
Okay.
So it could be something.
Conductivity.
Conductivity will imply that you're looking for conductive ions.
Yeah.
So if you have something completely inert, like very small particles of clay, that might not be conductive enough for the matter.
Pure water is less conductive than just your average water.
Okay. Okay. Gotcha.
Yes.
I'm not sure what the threshold's gonna be.
Sure.
Right, but you could potentially have dissolved things that are non-conductive there, which would sort. But that might be like a special corner case.
Okay. Gotcha. Well, thank you.
Mhm.
Appreciate it.
Now, not to create a mess.
Do you have any of this like the code that you're showing, or maybe the write-up of how to like maybe go about trying this on our own at home, anything like that?
I eventually plan to actually put most of this stuff actually online on my website. It's more of a time constraint thing. It just wasn't done before.
Yeah.
But if you want to just try out Fan there is obviously the simple XOR example that's available online. If you go to, I think, the Fan website there and look at examples there, that's the most common one. You could also find the same example written in PHP. So that would be a very simple thing. And once you get that concept, things kind of just fall in place. The harder part is figuring out, okay, how do you wire up your sensors there? That's a different topic.
Well, yeah, but that'd be useful for me too.
Yeah.
So you had a website?
Yes, it's on the bottom. Is this still? Oh, my slides are now.
Research?
Yeah, XY Research.
Okay. All right. Thank you so much.
How can we find your website?
Let's see. There's a chicken egg problem. It's on the bottom corner of my slides. I guess I'll put it back up. There.
Your head.
Right here. Now, I was going to show plots of like the individual sample readings, but I just ran out of time.
Actually, I thought this was supposed to be from 4:30 to 5:30.
Is it? I thought it was an hour. I was told it's like an hour.
Yeah, an hour, but I thought it started at 4:30.
Oh.
So I felt like, you still had. I thought you had like extra material, so you started early. When I clicked on the schedule, I think the time for your.
Oh, then this Tom came by at 4.
Yeah, and I guess you just wanted to just start.
I don't know. I just counted out half an hour. So I thought it was a little bit later than that, but I don't know.
They could have half an hour of extra time.
Yeah, that's your way of going about it.
So, you have 60 instances. I'm wondering just how much data, is too little. If you have 60 instances of two related numbers.
Right.
And you want to just see how, and then you have another, and then you have another one that's way out of, seems to be way out of a totally different relationship.
Right.
And you want to learn the
basically you have a series of 60 numbers, let's say 60 stock prices from 60 days ago. Right?
60 instances of, 60 instances, I'm thinking really of the elections. Okay? The popular vote and the electoral college vote.
Right, okay.
Okay? And they are related, sort of.
Okay, so basically you talk about 60 elections.
Yes.
Okay.
And you have popular vote and electoral college vote. And you train that. And then you apply it to the most recent election where there was a 3 million vote difference. And just to see how improbable that is.
You could probably do that there. I would think it'll be easier to just simply do a statistical analysis on that.
Oh, I see.
Because I think it's overkill. Yes, you could look for a pattern there. Basically, you're computing correlation between those two.
Yes.
But you could also do simple statistical analysis. You just talk about two different types of data coming in.
Okay.
So machine learning might be of an overkill tool.
Okay, thanks.
SCaLE 11.